Hello there, and welcome to the Cosmographer. Somewhere on this list is the reason our galaxy is silent, and the unsettling part is that nobody can tell you which entry it is. Number 10 is a supernova whose debris is sitting in the floor of the Pacific Ocean right now, drilled out and counted atom by atom. Number 8 is a self-replicating machine that ought to have reached every star in this galaxy within 40,000 years of being switched on, and that several deliberate searches of this solar system have failed to find. Number 5 argues that a world can evolve intelligence and never light a single fire because its air never crossed 18% oxygen. And the entry at number 1 predicts no evidence at all, for a reason that changes the meaning of every theory above it. 10 explanations for an empty sky, ranked by how much physical evidence each one leaves behind, counted down from 10 to 1. Get comfortable and settle in. If a slow, careful walk through 10 explanations for a quiet galaxy sounds like a good night to you, a quick like and subscribe helps this channel reach more curious minds like you. Because by the time we reach number 1, the question will not be what ended them. It will be whether anything has happened yet at all. Let's begin at number 10. Number 10, the supernovae that already reached us. The Milky Way is roughly 13.6 billion years old. It contains somewhere between 100 billion and 400 billion stars, and since the Kepler mission we have known that most of them carry planets. The working estimate from that survey is that about 1 in 5 sun-like stars hosts a roughly Earth-sized world at a temperate distance. Multiply that through, and the number of candidate planets in this galaxy alone runs into the billions. These are not contested numbers. They are the ordinary output of 2 decades of careful counting. Now set a second number beside them. A civilization with no exotic physics at all, using rockets no better than the ones we have already built, needs somewhere between 1 million and 100 million years to spread across a galaxy this size. The lower figure comes from a directed expansion, the higher from a slow random diffusion that assumes long pauses and no particular intent. Both are small, compared with 13.6 billion. The galaxy has had room for this to happen thousands of times over, with time left to spare. It has not happened, or if it has left nothing we can find. That gap has a name and a long literature, and this video is not going to spend 3 hours arguing about the name. This video asks a narrower question and a colder one. If civilizations arose in this galaxy and are now gone, what ended them? And, the question that organizes everything that follows, what should be left behind? That last question is the spine of this list. 10 theories, counted down from number 10 to number 1, ranked not by how likely they are and not by how frightening they are, but by how much physical evidence each one predicts we should be able to find. At the top of the countdown are theories whose debris has already been drilled out of the ocean floor and carried back from the moon. In the middle are theories whose evidence exists in principle and has been searched for and not found. Near the bottom are theories that leave nothing recoverable at all. And number 1 is the only entry on this list that predicts a completely empty record, for a reason that reframes everything above it. So at every entry we will ask the same plain question. What would this theory leave behind? And have we looked? We begin with the entry that answers it most concretely, because the answer is a jar of atoms. Iron-60 is a radioactive isotope of iron with a half-life of about 2.6 million years. That single number is the reason this entry opens the countdown. The solar system is 4.568 billion years old, which is roughly 1,700 half-lives. Any iron-60 present when the Earth formed decayed away to nothing long before the first living cell existed. So every atom of iron-60 found on this planet today arrived recently and arrived from somewhere else. It is a clock that cannot be reset and cannot be counterfeited, and it is the closest thing we have to a physical receipt for the death of a nearby star. The first detections came out of the Pacific. Klaus Knie and colleagues at the Technical University of Munich were working with ferromanganese crust dredged from the ocean floor, using a technique called accelerator mass spectrometry, which counts individual atoms rather than measuring bulk chemistry. They reported an anomaly in 1999 and confirmed it with a stronger signal in 2004, placing the deposition at roughly 2.8 million years ago. To appreciate what that measurement involves, consider that they were working with a few tens of atoms of iron-60 inside kilograms of rock. It is a little like identifying a handful of specific grains of sand on a beach and being certain they came from a different continent. In 2016, 2 papers published in the same issue of the journal Nature turned that anomaly into a map. Anton Wallner and colleagues at the Australian National University measured iron-60 in sediment cores drawn from the Pacific, the Atlantic, and the Indian Oceans. The signal appeared in all of them, which meant it was global rather than a local curiosity of one seabed. And it came in 2 distinct pulses. There is a broad peak somewhere between 1.7 and 3.2 million years ago, and an older, weaker one between roughly 6.5 and 8.7 million years ago. 2 separate deliveries, several million years apart. In the same issue, Dieter Breitschwert and colleagues at the Technical University of Berlin asked which stars could have sent them. Their modeling concluded that between 14 and 20 massive stars had exploded in the solar neighborhood over the last 13 million years. The 2 detonations most relevant to the iron-60 record occurred roughly 2.3 million years ago and roughly 1.5 million years ago, each at a distance of about 90 parsecs. 90 parsecs is a little under 300 light-years. That sounds like an enormous distance, and by the standards of everyday life it is. By the standards of this galaxy it is next door. 300 light-years is about 0.3% of the width of the Milky Way. It is worth explaining why this particular isotope is such a good witness. Iron-60 is manufactured in the shells of massive stars, by nuclei capturing neutrons one at a time over hundreds of thousands of years, and it is scattered outward when the star's core collapses and the outer layers are thrown off. There is no common alternative process that makes it in quantity. Ordinary stars do not produce it. Solar activity does not produce it. It is not a byproduct of anything that happens on Earth. So when it turns up in a sediment core, the list of possible explanations is short, and every item on that list is a dead star. Picture the delivery from underneath. On a Pliocene coastline roughly 2.5 million years ago, a new star appears in the sky. It brightens over days until it is far brighter than Venus, bright enough to read by, bright enough to cast a second set of shadows across the sand at night. Nothing on that shore reacts to it in any way that matters. The tide comes in on the same schedule. Whatever is living in the shallows carries on. Over the following months, the new star fades, and within a year or 2, the sky looks the way it always did. And the part that would actually matter has not arrived yet. The charged particles from that explosion are still in transit, wandering through tangled magnetic fields, and they will keep arriving in a slow drizzle for tens of thousands of years afterward, long after the light has gone, and long after there is anything left to associate the 2 events with each other. That separation is the strange, quiet fact at the center of this entry. The spectacle and the consequence travel on entirely different schedules. The record does not stop at the seabed. Gunter Korschenek's group found iron-60 in lunar samples returned by the Apollo missions, which matters because the Moon has no ocean chemistry, no biology, and no weather to complicate the story. Whatever fell on Earth also fell on the Moon, and the Moon kept a cleaner copy of the receipt. Dominic Cole and colleagues then found iron-60 in Antarctic snow deposited within the last 2 decades. That result is the one worth sitting with. It means the delivery is not a closed chapter of the past. The solar system is still moving through the debris field right now, today, and a few atoms of it are settling onto the ice every year. There is a fourth archive, and it is in orbit. The Advanced Composition Explorer, a spacecraft launched in 1997 to sample the particles arriving from interstellar space, detected 15 individual iron-60 nuclei over 17 years of operation. 15 atoms in 17 years is not a torrent. But because iron-60 decays on a 2 million-year clock, those 15 atoms cannot have traveled far. They imply a source within a few hundred parsecs, which is exactly where the seabed and the Moon said it was. The structure those explosions carved has a name. It is called the local bubble, and the solar system is inside it. It is a cavity in the interstellar medium, roughly 1,000 light-years across, filled with gas at about 1 million Kelvin and at a density of around 1 atom per 10 cubic centimeters. For comparison, the best laboratory vacuum on Earth is denser than that by a wide margin. The Sun drifted into this cavity somewhere between 5 and 10 million years ago, and currently sits near the middle of it, which is a coincidence of timing rather than a sign of any relationship. We are passing through a hole that something else made. In 2022, Catherine Zucker, Alyssa Goodman and colleagues used precise stellar positions from the Gaia spacecraft to map the walls of that cavity and found something worth pausing on. Essentially, every young star-forming region within about 200 parsecs of the Sun lies on the expanding surface of the local bubble. The shell of swept-up gas, piled up by roughly 15 supernovae, is the place where the next generation of stars in our neighborhood is being assembled right now. The graveyard and the nursery are, quite literally, the same object. That is not a metaphor about this video. It is a description of a wall of gas about 400 light-years from here, and we will come back to it at the end of the list. So the debris is real, the deliveries are dated, and the structure is mapped. The question this list keeps asking is what any of it means for the living, and for that we need a distance. The threshold most often quoted for serious biological damage sits at about 8 parsecs, which is roughly 26 light-years. A core collapse supernova at that range would strip a substantial fraction of the ozone column for several years, and the resulting rise in surface ultraviolet would damage the base of the food chain long before it troubled anything larger. That number has been the working figure for decades. Work published in 2023 by Ian Brunton, Connor O'Mahony, and Brian Fields extended the dangerous radius considerably, and the reason is worth understanding. A supernova that explodes into a dense cloud of interstellar gas does not simply flash and finish. The expanding shock keeps slamming into material and keeps producing X-rays for months and sometimes years afterward. That prolonged X-ray bath can deplete ozone out to something like 50 parsecs, which is over 150 light-years, a volume containing many more stars than the older figure allowed. There is a second mechanism, and it is stranger. Adrian Malott and Brian Thomas have calculated the muon dose from a supernova at about 50 parsecs. Muons are heavy relatives of the electron, produced when cosmic rays strike the upper atmosphere, and they are difficult to stop. They pass through hundreds of meters of rock and water without much trouble, which is why muon detectors are built deep underground, and why muons are used to image the interiors of pyramids and volcanoes. Their calculation suggests the ground-level muon flux would rise by a factor of several hundred in the years after the cosmic ray front arrived. And because muons penetrate, the dose scales with the size of the body absorbing it. In that scenario, the smallest organisms are barely affected, and the largest take the worst of it. That last detail connects to a specific event in the fossil record. Around 2.6 million years ago, squarely inside the Iron 60 window, the Pliocene marine megafauna extinction removed roughly a third of the large marine genera, including the shark Otodus megalodon. Catalina Pimiento and colleagues documented the scale of that loss in 2017. Mellott and Thomas proposed the muon connection the following year. It is important to be precise about the status of that proposal. It is a hypothesis with a suggestive coincidence of dates and a plausible mechanism. It is not an established finding, and there are competing explanations involving sea level and habitat loss. But the coincidence is real, and it is checkable, and the atoms sitting in the seabed are not in dispute. There is one more piece of geography to add, and it will matter later. The Sun sits about 8.2 kiloparsecs from the center of the galaxy, which is roughly 26,700 light-years. The supernova rate is not spread evenly across the Milky Way. In the crowded inner few kiloparsecs, stellar density is higher by orders of magnitude, and the frequency of nearby detonations rises with it. That observation produced the idea of a galactic habitable zone, developed by Guillermo Gonzalez, Donald Brownlee, and Peter Ward in 2001, and quantified by Charles Lineweaver, Yeshe Fenner, and Brad Gibson in the journal Science in 2004. Their estimate was that perhaps 10% of the stars in this galaxy sit in a band with enough heavy elements to build rocky planets and few enough catastrophes to let complex life persist. That estimate has been contested and revised in both directions ever since, and it should be held as one modeled number rather than a measurement. A reasonable question at this point is whether anything nearby is due. The answer is reassuring, and it is worth stating plainly because the popular version of this topic tends to leave it out. Betelgeuse, the red supergiant in the shoulder of Orion and the most discussed supernova candidate in the sky, is roughly 550 light-years away. That is comfortably outside every lethal estimate, including the extended one. IK Pegasi, at about 150 light-years, is the nearest plausible candidate for the other kind of stellar explosion, and it too is considered safe, and in any case is not expected to do anything for millions of years. As far as anyone can determine, there is no star within 50 light-years of the Sun capable of exploding at all. The two detonations that left Iron 60 in the seabed happened when this neighborhood contained young massive stars. It does not anymore. We are living in the quiet part of the cycle, on the inside of a cavity those stars carved before they finished. One more detail about the archive, because it shows how much a single core can answer. When Wallner's group went back to the same material in 2021, they measured plutonium-244 alongside the Iron 60. Plutonium of that kind is made in the violent process that builds the heaviest elements, and the amount they found was far too small relative to the iron for supernovae to be the main factory. That result argues that the gold and the platinum and the uranium in this planet came mostly from collisions between neutron stars, rather than from ordinary stellar explosions. It is an aside, but it is a useful one. The same handful of atoms in the same seabed answered a question about local extinction and a question about the origin of heavy elements at the same time, and answered them differently. So, have we looked? For this entry, uniquely, we did not have to look. It arrived. It settled into ocean sediment and lunar regolith and Antarctic snow, and we found it by accident while measuring something else. No theory further down this list will offer anything remotely as tangible. That is the shape of number 10. Somewhere between 14 and 20 stars have exploded in our neighborhood in the last 13 million years. At least 2 of them were close enough to leave their atoms in the ground beneath the ocean. Whether any of them ever ended anything more complicated than a plankton bloom is unknown and may stay unknown. But the mechanism is not speculative, the distances are not speculative, and the debris is not speculative. If the galaxy has been quietly removing its inhabitants, this is the only method on the entire list for which we hold the physical evidence in our hands. That is the most evidence any theory on this list will ever offer. From here, everything gets quieter. Number 9. The beam that leaves no scar. A supernova is what happens when a star runs out of fuel and falls inward. A gamma-ray burst is what happens when that collapse goes badly wrong in a very particular way, and it is not a larger version of the same event. It is a different kind of thing entirely. The recipe requires 3 ingredients. First, a star of more than roughly 20 solar masses, which is rare. Stars that large make up a tiny fraction of any population. Second, rapid rotation, which most massive stars lose over their lifetimes. Third, gas that is poor in heavy elements, because heavy elements drive strong stellar winds, and strong winds carry away the outer layers along with the star's spin. When all 3 conditions hold, the core collapses into a black hole, while the outer layers are still falling in. The infalling material piles into a disk around the new black hole, and the whole system launches 2 jets along the rotation axis at greater than 99.9% of the speed of light. The energy involved is difficult to hold in the mind, so it is worth building up to it carefully. If a long gamma-ray burst radiated its output in every direction equally, the total would be on the order of 10 to the 44th joules, released over a few tens of seconds. That is more energy than the Sun will emit across its entire main sequence lifetime of about 10 billion years. 10 billion years of steady output, compressed into roughly half a minute. The jets are narrow, which cuts that number down. A typical opening angle is a few degrees, so the true energy is smaller by a factor of somewhere between 100 and 500. But narrowness is not comfort. It means most bursts miss us entirely, and it means anything inside the cone receives the beam undiluted. The narrowing does not weaken the beam. It concentrates it. The proposal that one of these events shaped the history of life on this planet was published in 2004 in Astrophysical Journal Letters by Adrian Melott, Bruce Lieberman, Claude Laird, Larry Martin, Mikhail Medvedev, Brian Thomas, John Canizo, Neil Gerrels, and Charles Jackman. The title was a question rather than a claim. Did a gamma-ray burst initiate the late Ordovician mass extinction? The event they were asking about is one of the largest disruptions in the fossil record. The late Ordovician extinction happened roughly 445 million years ago. It is the second largest of the 5 great extinctions, removing something like 85% of species and around 60% of marine invertebrate genera. It did not happen all at once. It came in 2 pulses separated by several 100,000 years, with a severe glaciation between them, and the sequence of those events has been argued over for decades. The physical chain from a burst to a dead ocean is well characterized, and each link has been modeled. Gamma rays entering the upper atmosphere break apart molecules of nitrogen and oxygen. The freed atoms recombine into nitric oxide. Nitric oxide destroys ozone catalytically, meaning a single molecule can dismantle many ozone molecules in sequence before it is removed from the cycle. This is the same chemistry that made chlorine compounds so effective at thinning the ozone layer in the 20th century, running with a different reagent and at enormously greater intensity. Brian Thomas and colleagues put numbers on the result in 2005. A burst at 2 kiloparsecs, which is about 6,500 light-years, delivering 10 kilojoules per square meter, produces globally averaged ozone depletion of around 35%. In some regions, the depletion exceeds 50%. And it does not recover quickly. The nitrogen chemistry keeps working for years, so the depletion persists on a timescale of 5 to 10 years. What follows from that is straightforward and unpleasant. Surface ultraviolet B roughly doubles or triples. Phytoplankton live in the top few meters of the ocean because that is where the light is, and they have almost no ultraviolet defenses because in 4 billion years they have never needed any. The entire marine food chain rests on them. Damage the top few meters of the ocean for a decade, and everything above them in the chain runs out of food on its own schedule. There is a secondary product too, and it works in the opposite direction. Nitrogen dioxide is brown and opaque. Enough of it in the stratosphere reduces the sunlight reaching the surface, which cools the planet. That cooling has been proposed as a trigger for the Hernantian glaciation that accompanies the extinction. So the same event that opens the ultraviolet window can also, plausibly, close the sunlight one, and the fossil record of the late Ordovician does show both a biological crisis and a hard freeze. The detail that keeps this hypothesis alive, rather than merely interesting, is the selectivity of the kill. Shallow water and surface-dwelling planktonic organisms were hit disproportionately hard compared with forms that lived deeper. That is exactly the pattern ultraviolet damage predicts, because water absorbs ultraviolet quickly and a few meters of depth is real protection. It is not obviously the pattern a purely climatic explanation predicts, since cooling affects the whole water column. That asymmetry is suggestive. It is not proof, and the difference between those two words carries the whole weight of this entry. Let me put the moment itself in front of you, because the numbers do not convey what is strange about it. A shallow, warm Ordovician sea, 445 million years ago. The water is crowded in a way that would look alien and also perfectly ordinary. Trilobites moving across the sediment, graptolites drifting in colonies, brachiopods anchored in the shallows, and above all of them a haze of plankton filling the top few meters, thick enough to tint the water green. The beam has already passed. It took about 10 seconds, and it is already gone, and nothing at the surface registered its arrival. There was no sound, because there is nothing between here and there to carry sound. There was no flash at the surface, because the energy was absorbed high in the atmosphere. The sky at this moment looks exactly the way it looked yesterday. Over the following weeks, the quality of the light coming through begins to change in a way nothing alive is equipped to notice, and the top few meters of that ocean begin to fail, from the top down, in complete silence. There is no event to point at. There is a before, and there is an after, and there is nothing in between that anything could have seen. Which brings us to the reason this entry sits at number 9, rather than higher on a list ranked by evidence. When an asteroid ended the age of the dinosaurs, it left a signature. In 1980, Luis and Walter Alvarez found iridium at roughly 30 times the background level, in a thin clay layer, marking the boundary between the Cretaceous and the Paleogene, in Italy, and then everywhere else anyone looked. Iridium is scarce in the Earth's crust and common in asteroids, so the layer was a chemical fingerprint. The crater at Chicxulub was located afterward, in the 1990s, and the case closed. A gamma-ray burst leaves no such thing. It deposits no exotic element. It arrives, it rearranges atmospheric chemistry, it kills, and it leaves. And the atmosphere it rearranged has been completely replaced many times over since. The only plausible fingerprints are nitrate anomalies preserved in ice, and the oldest continuous ice on this planet covers roughly the last 800,000 years. Against 445 million, that is a rounding error. We are trying to read a record with the pages missing. This is where the entry earns its emotional weight, and it is worth slowing down for. The implication is not that a burst definitely happened. The implication is that a whole category of catastrophic event may have been occurring throughout the history of life on this planet, at intervals we cannot determine, and the rocks are structurally incapable of telling us. We could have been struck 3 times, or 30. There is no experiment that recovers the difference. Most of what we do not know about the past is a matter of not having looked hard enough, or not having the right instrument. This is a different kind of gap. It is a category of history that does not leave records, and we happen to be able to prove that it exists because we can watch it happening to other galaxies. The rate is the next question, and there is a real calculation behind it. Tzvi Piran and Raul Jimenez published a result in Physical Review Letters in 2014, working from the observed distribution of bursts and the metallicity of galaxies. Their estimate was that Earth has had roughly a 50% chance of experiencing a lethal gamma-ray burst within the last 500 million years. That is a coin flip across the entire span of complex animal life. They went further, and the further conclusion is the one that belongs on a list about dead civilizations. Because long bursts prefer environments poor in heavy elements, and because small galaxies are chemically poorer than large ones, roughly 90% of galaxies are too dangerous for complex life to persist. Only the outskirts of large, chemically enriched galaxies offer enough shelter. And because the universe as a whole was chemically poorer in the past, they concluded that for most of cosmic history, across most of the observable universe, sterilization events were frequent enough that complex life was probably not possible at all. Sit with the shape of that claim. It does not describe a galaxy that is killing civilizations. It describes a universe that spent most of its existence preventing them, everywhere except a few quiet suburbs, of which this is one. On that account, the Milky Way is not a graveyard because nothing was ever buried. It is a graveyard because the ground was salted for 10 billion years. One recent event gives all of this a scale a person can feel. On the 9th of October, 2022, a burst designated by its date arrived from about 2.4 billion light-years away. It was so bright that it saturated the detectors on the Fermi Gamma-Ray Space Telescope, which is to say the instrument built to measure gamma-ray bursts could not measure this one properly. It was recorded by instruments in China and in India. And from a distance of 2.4 billion light-years, a distance at which the galaxy that produced it is an unresolved smudge, it measurably disturbed the Earth's ionosphere, producing a detectable change in how very low-frequency radio waves propagate around the planet. Astronomers nicknamed it the brightest of all time. A burst of that class inside our own galaxy, pointed our way, would not be a curiosity for radio engineers. Now, an honest correction, because the standard version of this topic has been repeating a claim that is no longer supported. For years, the illustration of choice was WR104, a Wolf-Rayet binary system about 8,000 light-years away. It produces a spiral plume of dust that appeared in infrared images to be face-on, and a face-on spiral means we are looking down the system's rotation axis, which is where the jets would go. It was regularly described as a loaded gun aimed at Earth. Follow-up spectroscopy, including work led by Grant Hill using the Keck telescopes, found the orbital inclination is substantially tilted. The spiral looks face-on because of how the dust is illuminated, not because we are on the axis. The system is not aimed at us. It is worth correcting for its own sake, and it is worth correcting because it demonstrates something about this whole field. The frightening version of a claim travels much further than the follow-up that fixes it. It is also worth separating the two families of burst, because they are produced by completely different events, and only one of them belongs on this list. Bursts lasting longer than about 2 seconds are the collapsar kind described above. Bursts shorter than 2 seconds come from the merger of two neutron stars, and that was established rather than assumed. On the 17th of August, 2017, gravitational wave detectors recorded the inspiral of two neutron stars, and 1.7 seconds later, a short gamma-ray burst arrived from the same patch of sky. Telescopes on every continent turned to the location and watched the aftermath fade for weeks. It was the first time an event had been observed in gravitational waves and in light together, and it settled a decades-old question in about 2 seconds. The instrument that made the modern study of bursts possible is a small satellite named for a bird. SWIFT, launched in 2004, carries a wide-field detector that spots a burst and then rotates the entire spacecraft to point its telescopes at the position within about 90 seconds. Before SWIFT, a burst was a flash with a vague location and no follow-up. Since SWIFT, well over 1,000 have been pinned down precisely enough to identify the galaxy that hosted them. That is how we know the distances, and the distances are how we know the energies. Two details about the record should be held with appropriate caution. Nitrate spikes in ice cores have been proposed as a signature of both supernovae and bursts, on the reasoning that the same nitrogen chemistry that destroys ozone eventually rains out. Searches have been run. The results are ambiguous. Other processes produce nitrate, and the technique remains contested. And the observed rate of bursts is not the true rate. Because the jets are narrow, for every burst whose beam happens to cross the Earth, there are somewhere between 100 and 500 that occurred and missed. The sky is considerably busier than it looks, and always has been. Mellott and Thomas returned to the problem twice more, in 2009 and again in 2011, refining the biological damage estimates and working out how the ozone loss would vary with latitude. That kind of follow-up is the ordinary machinery of science, and it rarely makes the news, but it is the difference between a striking idea and a testable one, and this idea has now been examined for over 20 years without being either confirmed or discarded. Two more pieces of context, and this entry closes. The first is historical, and it is one of the better stories in 20th century astronomy. Gamma-ray bursts were discovered by accident, by satellites built to catch someone cheating. The Vela spacecraft were launched in the 1960s to monitor compliance with the Nuclear Test Ban Treaty by watching for gamma-ray flashes from clandestine detonations. They found flashes. The flashes were not coming from the Earth, and they were not coming from the Sun. Ray Klebesedel, Ian Strong, and Roy Olson published the discovery in 1973, once the data could be declassified. An instrument built for arms control found the most energetic explosions in the universe. The second is a small piece of good news. Because long bursts favor environments poor in heavy elements, and because the modern Milky Way has been chemically enriched by many generations of stars, our galaxy is now a comparatively poor factory for them. The conditions that produce collapsars were far more common in the early universe and remain more common in small, undeveloped galaxies today. Whatever the rate was when this planet was young, it is lower now. So, have we looked? Yes, in the only way available. We watch bursts in other galaxies at a rate of roughly 1 per day, we model what one would do to an atmosphere like ours, and we search terrestrial records for a fingerprint we have every reason to believe was never left. The searching is real, and the answer is genuinely empty, and this time, the emptiness proves nothing at all. But the next theory does not depend on anything exploding. It depends on something that was built, and on the fact that it should be sitting in this solar system right now. Number 8. The machines that should already be here. In 1948 and 1949, John von Neumann gave a series of lectures on a problem that had nothing to do with space travel. He wanted to know what a machine would need, logically, in order to build a copy of itself. The work was published posthumously in 1966, edited by Arthur Burks, under the title Theory of Self-Reproducing Automata. Von Neumann's central insight was that self-replication requires two things working together: a universal constructor capable of building anything from a description, and a description of the constructor itself. And crucially, the description has to be used in two entirely different ways. It has to be executed, so the machine gets built. And it has to be copied blindly without being interpreted, so the copy has a description too. He worked that out several years before anyone understood the relationship between DNA and protein. It is one of the more remarkable pieces of anticipation in the history of science. A mathematician deduced the logical architecture of heredity from first principles at a desk, without a biological sample anywhere in the building. He was not writing about spacecraft. Nearly everyone who has used his argument since has been. The engineering study came in 1980. A joint summer study, run by NASA and the American Society for Engineering Education, held at Santa Clara and documented in NASA Conference Publication 2255, was largely written up by Robert Freitas. It designed, in real detail, a self-replicating factory for the surface of the Moon. A seed unit weighing about 100 tons would land, unfold a solar array, and begin processing lunar regolith. It would separate out silicon, aluminium, iron, and oxygen. It would fabricate structural components, then electronics, then the tools to make more tools. The study's central technical question was what they called closure, whether the system could make every part of itself from local material or whether some component would always have to come from Earth. Their conclusion was that closure was achievable and that the factory could double itself in roughly 1 year. In the same year, Freitas published a design in the Journal of the British Interplanetary Society for the interstellar version. It was derived from Project Daedalus, the fusion starship study the same society had run between 1973 and 1978, 50,000 tons at launch, 12% of the speed of light, a 50-year cruise to Barnard's star. Freitas's variant would arrive at a target system, settle into orbit around a gas giant's moon, mine it, and build copies of itself to send onward. It is worth appreciating how hard the closure requirement actually is, because it is the one genuine obstacle in the whole scheme. A modern integrated circuit is the product of a supply chain spanning dozens of countries, hundreds of specialized materials, and equipment that itself requires other equipment to build. A self-replicating factory has to collapse all of that into one machine standing on a rock. The 1980 study got around this by allowing the factory to be enormous and slow, and to use crude components, vacuum-deposited electronics rather than photolithography, cast metal rather than machined alloys. The result would be a poor computer by our standards and a perfectly adequate one for the task, which is the point. Replication does not require the best technology available. It requires the simplest technology sufficient, repeated without error, indefinitely. Now the arithmetic, which is the reason this entry is uncomfortable. Suppose a probe crosses to a neighboring star. Suppose it is slow, most of a millennium in transit, plus decades or centuries on arrival to mine, refine and build. Call the whole cycle 1,000 years. And suppose it builds only 2 successors, which is a conservative assumption for a machine with an entire solar system of raw material and no deadline. Doubling every 1,000 years, after 10,000 years there are about 1,000 probes. After 20,000, a million. After 30,000, a billion. After 40,000 years, there are roughly 1.1 trillion. The Milky Way, on the high estimate, has 400 billion stars. The fleet exceeds the entire target list by a factor of 2.5, and it does so in 40,000 years, a span shorter than the interval since the last ice age reached its maximum. Not shorter than the age of the galaxy. Shorter than the age of cave painting. This argument did not begin with Tipler. Michael Hart published the paper that started the modern conversation in 1975, also in the Quarterly Journal of the Royal Astronomical Society. Hart's calculation was cruder, and its conclusion was the same. With plausible ship speeds and plausible pauses between settlements, a single expanding civilization crosses the galaxy in about 2 million years. His point was that 2 million years is so short relative to the age of the galaxy that the absence of anyone here requires an explanation, and that the explanations available all cost something. Every argument in this entry is a descendant of that paper. Frank Tipler pressed this into a formal argument in 1980 in the Quarterly Journal of the Royal Astronomical Society under a title that did not hedge: Extraterrestrial intelligent beings do not exist. His reasoning was that self-replicating probes require no physics we do not already have, that any technological civilization would eventually build them, that they would saturate the galaxy in a geological instant, and that their absence is therefore not weak evidence of absence but conclusive evidence of it. Carl Sagan and William Newman replied in 1983 in a paper usually referred to by its subtitle about the solipsist approach to extraterrestrial intelligence. Their objection was not mathematical, but behavioral. A civilization advanced enough to build self-replicating machines would be advanced enough to understand what releasing them into a galaxy means, and would therefore decline to do it. They had also published a diffusion model in 1981, which produced a much slower colonization time, on the order of 100 million years rather than a million, because it modeled expansion as a random walk, with population pressure rather than as a directed front. The disagreement between Tipler and Sagan is the disagreement this entry has never resolved. Is expansion an engineering question or a decision? The modern version of the calculation is more careful and does not rescue anybody. In 2019, Jonathan Carroll Nellenbach, Adam Frank, Jason Wright, and Caleb Scharf published a settlement model in the Astronomical Journal that added a factor the older work ignored: stars move. The galaxy is not a fixed lattice of targets. It shears, it rotates differentially, and over hundreds of millions of years it stirs itself thoroughly. A settlement front that expands slowly is carried around the galaxy by orbital motion regardless. Their result was that even with ships traveling at 10 kilometers per second, slower than several probes humanity has already launched, and even with long dormant periods between settlements, the galaxy fills in well under 1 billion years. But their paper contains a second conclusion that deserves equal weight, and it complicates the whole entry. They found that the Milky Way could be substantially settled and still look empty to us. Settlements could be sparse. Nearby systems could have been visited and abandoned long ago. And we have been looking in any serious way for about 65 years at a small number of stars in a narrow set of wavelengths. An empty sky is compatible with a settled galaxy if the settlement is thin enough and old enough. The variant that puts this entry on a list about the dead adds one line of code. The term comes from fiction. Fred Saberhagen began writing stories in 1963 about self-replicating war machines, built by a civilization long since destroyed, still executing their instructions. The word entered the technical literature through David Brin's 1983 review in the Quarterly Journal of the Royal Astronomical Society, a paper called The Great Silence, that catalogued roughly 30 proposed explanations for the absence of anyone. Brin's observation about deadly probes was structural rather than dramatic. Most explanations for the silence require every civilization to behave the same way, which is implausible for any large population. This one does not. It requires exactly one civilization to have been hostile and capable, once, at any point in 13 billion years. And the builders do not need to survive. This is the feature that makes the idea persistent. A fleet of self-replicating machines with a suppression instruction does not need its authors. It does not need a reason. It does not need to be maintained. It only needs to have been launched and then to keep working, which is what machines built by careful engineers do. There is one more feature of this scenario that separates it from everything else on the list. Every other theory here requires a coincidence of timing. A supernova has to happen while someone is nearby. A civilization has to be transmitting while someone else is listening. A window has to overlap with a window. This one does not. A self-replicating fleet is a solution to the timing problem because it does not care when anything happens. It waits. If the machines exist, the fact that we are separated from their builders by 10 billion years is not an obstacle to encountering them. It is irrelevant. So, have we looked? This is the entry where that question has the most concrete answer on the entire list, because the evidence is supposed to be here rather than out there. And the searches are specific and are worth naming. Robert Freitas and Francisco Valdez searched the Earth-Moon Lagrange points photographically in 1980 and again in 1983 using the Leuschner Observatory. Those points are gravitationally stable parking spots where an object can sit indefinitely without expending fuel, which is exactly where a patient observer would want to be. They found nothing down to their limiting magnitude. Later, wide-field surveys, including pan-stars, have pushed those limits considerably deeper. Beatriz Villarroel's Vasco project takes a different approach. It compares photographic plates from the middle of the 20th century against modern digital sky surveys, hunting for point sources that were present then and are absent now. Objects do not usually vanish. Anything that has would be worth explaining. Breakthrough Listen has surveyed more than 1 million nearby stars and about 100 galaxies at radio wavelengths. A 2020 survey using the Murchison Widefield Array in Western Australia covered roughly 10 million star systems in the direction of the Vela constellation and returned no technosignature. The survey, led by Jason Wright and colleagues from 2014, went further out still. It examined about 100,000 galaxies in infrared data from the WISE spacecraft, looking for the waste heat that galaxy-spanning engineering would necessarily radiate. No galaxy in that sample showed the expected excess. Every one of those searches came back empty, and every one of those empty results is a genuine measurement rather than a shrug. That is what makes this entry sit as high as it does. It is also worth being honest about how hard the search is, and the easiest way is to picture the target. An object in the asteroid belt, 10 meters across, sitting at thermal equilibrium with sunlight. It is not cloaked and it is not concealed. It has simply been switched off for a very long time and has no reason to move. Its temperature matches the rock beside it, because everything at that distance from the Sun settles to the same temperature. Its brightness is whatever its surface reflects, which after a few 100 million years of micrometeorite weathering is roughly whatever the rock beside it reflects. Every asteroid survey ever run has swept that volume of sky and recorded nothing there, either because there is nothing or because there is, and at our current resolution, the two possibilities produce exactly the same image. That is the strange position this entry leaves us in. The null result and the positive result look identical, and will keep looking identical until something moves. The nearest thing to a test case in living memory arrived on the 19th of October, 2017. Robert Werrick, working with the Pan-STARRS 1 telescope on Haleakala, spotted an object moving too fast to be bound to the Sun. It was the first confirmed visitor from interstellar space, and it was odd in several ways at once. Its brightness varied by a factor of about 10 as it tumbled, implying a shape far more elongated than any asteroid catalogued in this solar system. It showed no dust tail and no gas emission, so it was not behaving like a comet. And as it left, it accelerated slightly more than gravity alone accounted for, which is normal for a comet venting material and difficult to explain for a rock that is visibly not venting anything. Those anomalies produced a proposal, from Abraham Loeb among others, that the object might be artificial, a thin sheet pushed by sunlight. It is worth being careful and calm about where that stands. The proposal is a minority position. The explanations most researchers favor are natural, a fragment of nitrogen ice from the surface of a body like Pluto, or an extremely porous aggregate of dust with a very low density, either of which would produce the acceleration without any technology. Two more interstellar objects have been found since, and neither has been unusual in the same way. The honest summary is that the first interstellar visitor we ever saw was strange, that strange is not the same as engineered, and that the episode demonstrated mainly how little we could learn from an object we noticed on its way out. There is one honest correction that has to be made here, because the popular version of this story gets it backwards, and the mistake changes the emotional shape of everything that follows. The usual framing is that humanity has been broadcasting loudly for over a century, that a bubble of our radio and television transmissions, 125 light-years across, is now sweeping past thousands of stars, and that anyone within it already knows about us. The bubble is real. The signal inside it is not readable. Abraham Loeb and Matthias Saldarriaga calculated this in 2007. An instrument like LOFAR, a large low-frequency radio array, could detect Earth-level broadcast leakage out to a few light-years. Not a few hundred. A few. Ordinary transmissions are not aimed, they spread in all directions, and their intensity falls with the square of distance until they sink below the natural radio noise of the galaxy, which happens almost immediately on interstellar scales. The genuinely loud things humanity has done are brief and pointed. Planetary radar, used to map the surfaces of asteroids and planets by bouncing a beam off them, concentrates enormous power into a narrow cone. The Arecibo telescope in Puerto Rico did this for decades, until its cables failed and its platform collapsed on the 1st of December, 2020. The Goldstone antenna in California still does. Those transmissions were narrow, short, and aimed at rocks in our own solar system. So the image of a steadily expanding sphere of legible human broadcasting arriving at one star system after another is wrong on the physics. It is a comforting kind of wrong and an unsettling kind of wrong at the same time. It means we have not announced ourselves nearly as loudly as the folklore says. It also means that if a machine were waiting for a species to become detectable by radio, it would still be waiting. there is a final wrinkle worth carrying forward. Robert Freitas raised a question about what such a probe would actually do on noticing something, whether it would report continuously or only on a trigger. The difference is not academic. A probe that reports continuously implies a network and a recipient. A probe that reports only when a threshold is crossed implies a criterion, set once, by someone who may no longer exist. And a fleet older than 1 billion years would not be the fleet that was launched in any case. Copying introduces errors, errors accumulate, and several researchers have argued that a self-replicating fleet would drift, diverge, and effectively evolve. Whatever instructions were written at the beginning would be, by now, something the authors would not recognize. There is a quiet irony in all of this that is worth naming before we move on. Von Neumann worked out the logic of self-replication as a piece of pure mathematics, and the first physical system anyone confirmed to match his architecture was not a machine at all. It was the cell. Every organism on this planet is a universal constructor, carrying a description of itself, copying that description blindly and executing it separately, exactly as he specified. Which means the galaxy already contains self-replicating probes in enormous numbers. They are just very small, they travel slowly, and so far they have only colonized one world. The next theory keeps the intent and removes the machine entirely. Its evidence is not in the asteroid belt, and it is not on the moon. It is in every cell of your body. Number 7. The message inside us. In 1973, in volume 19 of the journal Icarus, 2 scientists published a 6-page paper with a title that reads like a provocation and was not intended as one. It was called Directed Panspermia, and the authors were Francis Crick and Leslie Orgel. The names matter here. Crick had co-authored the description of the structure of DNA with James Watson, published in Nature in April 1953, a paper of roughly 900 words that reshaped biology, and shared the Nobel Prize for it in 1962. Leslie Orgel, working at the Salk Institute, was one of the founders of what became the RNA world hypothesis, the leading account of how self-copying chemistry could have preceded proteins. These were not people on the margins of the field. They were the people who had built a good part of the field's foundation. Their proposal was that life on Earth may have been placed here deliberately by a technological civilization elsewhere in the form of microorganisms sent across interstellar space. And their stated reason for publishing was almost as interesting as the idea itself. They argued that the hypothesis was being ignored, not because it had been examined and rejected, but because it sounded like the wrong kind of question, and that this was a poor reason for science to decline to look at something. The idea they were modifying was much older. In 1903, the Swedish chemist Svante Arrhenius proposed that spores could drift between star systems pushed by the pressure of starlight. Panspermia without a sender, life spreading the way dandelion seeds spread. The objection to that version was raised almost immediately and has never been answered. Ultraviolet light and cosmic rays would sterilize an unshielded spore long before it crossed the gap. A journey between stars at any speed sunlight can supply takes tens of thousands of years, and nothing biological survives tens of thousands of years of unshielded radiation. Crick and Orgel's modification was to add an engineer. If the transfer is deliberate, the spores can be shielded, aimed, concentrated, and sent in numbers. Every objection to the passive version dissolves the moment someone is packing the cargo. That is the entire content of the word directed in the title, and it converts an idea that does not work into one that merely cannot be tested. They made 2 arguments. One has held up. One has not. The first is the universality of the genetic code. Every organism that has ever been examined on this planet uses the same system, 64 three-letter codons, built from 4 bases, mapping onto 20 amino acids and a set of stop instructions. A bacterium in a hot spring, an oak tree, a jellyfish, and a human being all run the same underlying encoding. There are minor variants. Mitochondria use a slightly altered set of assignments, and so do a few unusual lineages of single-celled organisms. But the core mapping is shared by everything. Those variants are themselves informative, and they cut gently against the argument being built on top of them. They show that the code is not frozen solid. It can be altered, in small ways, by ordinary evolutionary processes, which means its uniformity across the tree of life is a fact about shared ancestry rather than a fact about chemical necessity. That is exactly what the seeding hypothesis wants, and it is also exactly what a single terrestrial origin predicts. Crick and Orgel's point was that this is what you would expect from a single origin, and not what you would expect from many. If life had arisen repeatedly and independently on the early Earth, in different pools under different conditions, you would expect surviving descendants of more than one of those origins, running incompatible codes. We do not see that. Every living thing is a relative. On its own, that is not evidence of seeding. A single terrestrial origin explains it just as well, but it does establish that whatever happened, happened once. Their second argument concerned molybdenum. Molybdenum is essential to a number of enzymes, most importantly, nitrogenase, the enzyme that lets certain bacteria pull nitrogen out of the air and make it available to everything else. And molybdenum is comparatively scarce in the Earth's crust, at something around 1 part per million. Crick and Orgel suggested that biology's reliance on a rare element might indicate that it was optimized somewhere richer in it. That argument should now be retired, and the script of this video is going to retire it plainly. Molybdenum is highly soluble in oxygenated seawater, and in the ocean it is among the more available trace metals, considerably more available than iron, which life also depends on. Crustal abundance is the wrong measure. The organisms that need molybdenum live in water, and in water it is not scarce. It is a good example of a reasonable inference drawn from the wrong reference frame, made by 2 extremely careful people, and it is worth saying so calmly rather than pretending the paper was flawless. The timing argument is the one that has strengthened since, and it did not come from Crick and Orgel at all. It came from geology. The Earth formed about 4.54 billion years ago and was not habitable for a substantial period afterward. The oldest widely accepted microfossils come from the Strelley Pool Formation in the Pilbara region of Western Australia and are about 3.5 billion years old. Carbon isotope ratios in graphite from Isua in Greenland suggest biological carbon fixation as early as 3.7 to 3.8 billion years ago, because living processes prefer the lighter isotope and leave a measurable signature. And in 2015, Elizabeth Bell and colleagues reported graphite inclusions inside a zircon crystal from the Jack Hills with a biological isotopic signature at 4.1 billion years, a claim that remains genuinely debated. Take even the most conservative of those dates. Life appears within a few 100 million years of the planet becoming capable of hosting it. Whatever the origin of life is, it was not a slow process here. It looks less like a lottery that took a long time to win, and more like something that happened almost as soon as it was permitted. Which cuts both ways, and the most substantial recent evidence cuts against the seeding hypothesis rather than for it. In 2024, Edmund Moody and colleagues published a molecular clock analysis in Nature, Ecology and Evolution, examining the last universal common ancestor, the organism from which every living thing descends. Their result, placed it at roughly 4.2 billion years ago, earlier than most previous estimates. And their reconstruction described it as already complex, a genome of around 2,500 protein families, an anaerobic metabolism, and the beginnings of an immune system, which implies it was already living in a community and already being attacked by viruses. So life was not merely early. It was early, sophisticated, and embedded in an ecosystem. That is compatible with seeding. A seeded organism would arrive pre-built. It is at least as compatible with a fast terrestrial origin, followed by rapid diversification. Honesty requires putting both readings side by side and not choosing between them on the basis of which is more interesting. Now, the reason this belongs on a list about the dead, because the general version of panspermia has nothing to do with anyone dying. The specific scenario is this. A civilization has determined that it is ending. Not threatened, ending on a schedule it cannot alter. Colonization is not available to it, because colonization requires a future. It requires arrival, construction, generations. What such a civilization can do is much cheaper. Microorganisms weigh nothing. They need no life support, no crew, no arrival date, no signal, no reply. A dying civilization with a spacecraft and a catalogue of nearby planets with plausible chemistry can seed dozens of them, and none of the seeds needs to succeed for the effort to have been worth making, and nobody who launched them will ever know whether any did. It is a scenario in which the graveyard produced an heir instead of a monument. Which is the only version of a dead civilization on this entire list where anything at all continued. And there is an extension of the idea that gives this entry its genuinely unsettling edge, one that must be handled carefully because it is contested and has not been accepted. In 2013, in the same journal that published Crick and Orgel 40 years earlier, Vladimir Sherbak and Maxim Makukov argued that the standard genetic code contains arithmetic regularities that they considered too ordered to be accidental. Their claim concerned patterns in nucleon counts across the codon table, the numbers of protons and neutrons in the amino acids, arranged in symmetries and repeated multiples that they said would not arise from chemistry alone. The proposal was that the code is not only a mechanism, but also a medium, that a message could be written into it, and that it would then be copied faithfully into every descendant organism on the seeded world, for as long as life persisted there, waiting to be read by anything that eventually learned to read. Set aside the question of whether it is true, and consider only why anyone would try it. Every other method of leaving a record has a shelf life. A monument erodes. A radio signal passes and is gone. A spacecraft decays under micrometeorite bombardment over hundreds of millions of years. A message written into the genetic code of a living population has a property none of those have. It is copied, continuously, by every organism that reproduces, and it is proofread by machinery that has been optimized for accuracy over billions of years. It is the only archive that maintains itself, and it maintains itself for as long as anything on the planet is alive. The paper has been criticized substantially, and the criticism is fair. The patterns depend on particular choices about how to count and how to order the table, and no independent group has confirmed that the regularities survive alternative reasonable encodings. It is generally regarded as numerology rather than a result. That is the honest status, and this video is not going to soften it. But there is a second observation that survives regardless of what one makes of that paper, and it is worth stating slowly. We produced a draft of the human genome in 2001. We declared it essentially complete in 2003, and that declaration was quietly wrong. Substantial regions were unreadable with the technology of the time, and it was not until 2022 that the Telomere to Telomere Consortium published a genuinely gap-free sequence, 3.1 billion base pairs. Roughly 1 to 2% of it codes for protein. The function of a great deal of the remainder is still being worked out, and new functional elements are still being identified in regions that were once dismissed as inert. That is not evidence of a message. It is simply the accurate state of our reading ability, and the accurate state is that we finished the transcription about 3 years ago and are still learning the language. The last piece is whether the delivery is physically possible, and here the answer is a qualified yes. Microorganisms can survive transfer between planets inside rock. This is the case that Fred Hoyle and Chandra Wickramasinghe argued for decades, and the transfer mechanism itself is not in doubt. The Martian meteorite recovered in Antarctica in 1984 demonstrated that material does move between worlds. The famous claim of fossilized microbes inside it did not survive scrutiny, but the journey did. Interstellar distances are harder. The Tampopo experiment, run on the exterior of the International Space Station, exposed pellets of the radiation-resistant bacterium Deinococcus radiodurans to open space for 3 years. The outer cells died and, in dying, shielded the ones beneath them, and the survival curve implied that an aggregate a fraction of a millimeter thick could last for years in that environment. Years is enough to cross a solar system. It is not obviously enough to cross between stars, which takes tens of thousands of years at minimum without shielding and design. Shielding and design, of course, is precisely what this theory proposes. And it is worth noting that we have already come close enough to doing this ourselves that there are rules about it. The Outer Space Treaty obliges spacefaring nations to avoid harmful contamination of other worlds, and NASA and the European Space Agency maintain planetary protection offices whose job is to ensure that a spacecraft landing on Mars or flying through the plume of Enceladus is not carrying a viable terrestrial passenger. Landers are baked, assembled in filtered clean rooms, and given bioburden budgets measured in spores per square meter. The Galileo probe was deliberately destroyed in Jupiter's atmosphere in 2003, and Cassini was destroyed in Saturn's in 2017, in both cases specifically so that they could not eventually drift onto a moon with liquid water. Accidental directed panspermia is not a philosophical scenario. It is an engineering line item with a budget. The technology that would make deliberate seeding possible within an institutional lifetime is also no longer purely notional. The breakthrough Starshot concept proposes gram-scale sails accelerated by a ground-based laser array to something like 20% of the speed of light, a crossing to the nearest star in about 20 years rather than tens of thousands. Nothing about that concept is close to being built, and several of its engineering problems have no current solution. But the payload mass it assumes is roughly the mass of a paperclip, and a paperclip is far more than enough room for a great many bacteria. Crick returned to these questions at book length in 1981, in a volume called Life Itself, and the tone of that book is worth noting because it is not the tone of an advocate. It is the tone of someone laying out a possibility, stating its weaknesses, and asking that it not be dismissed on grounds of taste. So, have we looked? In a sense, we have been looking at the evidence continuously since 1953, without treating it as evidence. It is not on a distant world. It is not in the asteroid belt. It is in the sequence of every organism on this planet, including the one listening to this. And the honest conclusion, which is less dramatic than the theory deserves and more interesting than a dismissal, is that directed panspermia is not falsifiable in its general form, that relocating the origin of life to another planet does not explain the origin of life, and that both of those objections were understood by Crick and Orgel when they wrote the paper. Crick himself moved away from the idea in later decades, as the RNA world hypothesis matured and made a terrestrial origin look more achievable. Watching one of the most consequential biologists of the 20th century propose something strange, argue for it seriously, and then set it down when the evidence moved is not a failure of the idea. It is what the process is supposed to look like. The next theory does not think anyone left a message for us. It thinks the reason for the silence is that a message is the most dangerous thing a civilization can send. Number 6. The forest that never shows a kill. Everything above this point on the list has been measurement. Isotopes in seabed cores, photon energies, ozone chemistry with reaction rates, sequenced genomes. This entry is not measurement. It is game theory, and it is worth marking the transition clearly rather than sliding across it, because the two kinds of argument feel similar and are not. What follows is reasoning about what rational agents would do under specified conditions. It can be examined, and it can be argued with, and it cannot be checked against an instrument. The best-known formulation belongs to the Chinese writer Liu Cixin in a novel published in 2008 and translated into English by Joel Martinson in 2015. The structure of the argument is compact enough to state completely. It rests on two axioms. First, survival is the primary need of any civilization. Second, the total matter in the universe is finite, while civilizations tend to grow. And it derives two consequences from them, which are the parts that actually do the work. The first is the chain of suspicion. Across interstellar distances, no civilization can verify another's intentions. A message takes years or centuries in each direction, so there is no conversation, only a sequence of monologues separated by lifetimes. And the problem compounds. You cannot know what they believe about you. You cannot know what they believe you believe about them. Each additional layer of that regress requires resolution before any cooperative move becomes rational, and there is no mechanism at interstellar range for resolving even the first one. On Earth, trust between strangers is built through repeated interaction, shared institutions, and the ability to observe consequences. None of those exist between star systems. The second is the technological explosion. A civilization's capability can leap discontinuously in far less time than a signal takes to cross between stars. Which means an assessment expires. If you determine that a neighbor 400 light-years away is harmless, your determination describes them as they were 400 years ago, and 400 years is long enough for a civilization to become something entirely different. Our own 400-year window ran from before the first telescope to the present, and included every industrial and computational revolution in our history. It is worth walking one round of that reasoning slowly, because the abstraction hides how ordinary each step feels. Suppose a signal is confirmed from a system 200 light-years away. The first question is not whether they are friendly. It is what they were like 200 years ago, because that is the only period the signal describes. The second question is what they are like now, which is unanswerable. The third is what they will be like in 400 years, when a reply could arrive, and that is the only question that has any bearing on a decision. Every step is reasonable. The sequence ends nowhere. Put those two together, and the argument concludes that the rational move on detecting another civilization is to eliminate it, and that the rational posture otherwise is silence. Hence the image the novel is named for, a forest at night, full of armed hunters, all moving as quietly as they can. Anyone who calls out reveals a position. Nothing else about them is knowable, so position is the only information that gets transmitted, and position is exactly the information a hunter needs. The idea did not begin in fiction, and it is worth crediting the technical lineage. David Brin's 1983 review in the Quarterly Journal of the Royal Astronomical Society, the same paper that gave the previous entry its framing, laid out the structure of the danger argument and made an observation about it that most treatments miss. Most explanations for the silence require every civilization to behave the same way, and uniform behavior across a large population is a very strong assumption. This one does not. It requires only that the possibility of a hostile civilization cannot be excluded, which is a much weaker requirement and correspondingly harder to escape. Greg Bear dramatized the scenario in a novel in 1987, and Beatriz Gatto Rivera restated it in technical form in 2006. Set against all of this, there is a real event, on a real date, that this argument makes complicated. On the 16th of November 1974, the Arecibo radio telescope in Puerto Rico transmitted a message toward the globular cluster Messier 13, roughly 25,000 light-years away. The message was 1,679 bits long, and the number was chosen deliberately. 1,679 is the product of two prime numbers, 23 and 73, which means the bits can be arranged into a rectangle in exactly two ways, only one of which produces a coherent picture. It is a puzzle with a built-in instruction manual. The picture encoded the numbers 1 through 10 in binary, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the chemical formulae of the nucleotides of DNA, the double helix itself, a human figure with its height, the population of the Earth, a diagram of the solar system with the third planet raised, and finally the telescope that sent it, with its dish diameter. It was broadcast at 2,380 megahertz, with an effective radiated power in the region of 450 kilowatts, and it lasted under 3 minutes. For those 3 minutes it was, at that frequency, by a very wide margin, the brightest object in the galaxy. It was also ceremonial, and everyone involved knew it. Messier 13 will not be where the telescope was pointing when the message arrives in 25,000 years. The cluster and the sun will both have moved. Frank Drake, who designed it, described it as a demonstration of capability rather than an attempt at contact. It was a way of marking the completion of a major upgrade to the telescope, which is a thoroughly human reason to do something that lasts 25 millennia. There is something worth sitting with in that. The telescope that sent the message is gone. Its suspended platform came down in December of 2020, after decades of service and a series of cable failures, and the dish beneath it was destroyed. The message it sent in 1974 is currently about 51 light-years out, which is roughly 1/500th of the way to its destination, and it will keep going for another 25,000 years. The instrument outlived by its own transmission by a factor of 10,000, a ratio that is worth remembering every time this topic is discussed, as though transmission were a reversible decision. Other transmissions followed and were less ceremonial. The cosmic call messages went out from the Evpatoria antenna in Crimea in 1999, and again in 2003. The teenage message followed in 2001. A message from Earth was aimed at a planet orbiting the star Gliese 581 in 2008. Lone Signal ran in 2013. A proposal called Beacon in the Galaxy was published in 2022. There is also the material we sent physically rather than by radio, which nobody debates because it is so slow as to be almost symbolic. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, carry engraved aluminium plaques showing two human figures, the hydrogen transition, and a map of the Sun's position relative to 14 pulsars, a set of navigational beacons chosen because their spin rates are precise and slowly changing, so the map doubles as a timestamp. The Voyager probes, launched in 1977, carry gold-plated copper phonograph records holding 115 images, greetings in 55 languages, and 90 minutes of music. Those objects will still be intact and readable in 100 million years, long after every radio transmission has dispersed, and long after the telescope that sent the Arecibo message has crumbled. They are also moving so slowly that they will not pass near another star for tens of thousands of years, and the pulsar map, engraved with such care, points at a location the Sun will have left. The practice has a name: messaging extraterrestrial intelligence, and it has been contested from inside the field rather than from outside it. In 2015, a statement signed by a range of scientists and public figures, including David Brin, argued that deliberate transmission is a decision with planetary consequences and that no small group of researchers is entitled to make it unilaterally on behalf of everyone. Stephen Hawking's much-quoted remark from 2010, comparing a visit from an advanced civilization to Columbus's arrival in the Americas and noting that it did not go well for the people already there, belongs to the same conversation. Now the counter-argument, which is serious, and which this video is going to give its full weight, because the frightening version of this entry travels much further than the careful one. Destruction is observable. A relativistic projectile crossing interstellar space, a star being manipulated, or the abrupt extinction of a technosignature would all be visible across enormous distances. Any civilization that eliminated another would, in the act, reveal its own existence and approximate position to every remaining observer in a very large volume. That is not a free action. It is an announcement, which produces a deterrent structure rather than a free-fire zone. If striking reveals you, then the safest thing a hunter can do is not hunt, and the equilibrium becomes mutual silence with nobody actually shooting. Robin Hanson and others have made the sharper version of this point. Preemption is not an evolutionarily stable strategy when detection is symmetric, because the aggressor's advantage is smaller than the intuition suggests, and the exposure is larger. But the equilibrium is fragile. It holds only if every participant is rational, patient, and confident that no one else will move first. One impatient participant, once in 13 billion years, collapses it. So the honest state of the argument is not that hunters are known to exist. It is that the stable outcome and the catastrophic outcome are separated by a single decision made by somebody nobody can see, and there is no way to determine from here which way it went. There is a further weakness in the argument that deserves stating because it applies to every treatment of this idea, including the most careful. Game-theoretic models of this kind assume perfect rationality and symmetric information. Neither assumption survives contact with anything real. Actual decision-makers act on incomplete information, under institutional pressure, with limited time, and frequently in ways that are afterwards difficult to reconstruct. A conclusion that depends on every participant across 13 billion years behaving as an idealized optimizer is not a strong conclusion. It is an interesting one. And there is one detail about the mechanics that undercuts the hunting version specifically. A projectile traveling at a large fraction of the speed of light arrives almost simultaneously with the light announcing its departure, which sounds like the perfect weapon and is in fact a problem for the attacker. The launch itself is an enormous energetic event. Accelerating any substantial mass to relativistic speed requires releasing energy on a scale that is visible across the galaxy, and it is visible immediately, in all directions, to everyone except the target. The strike is invisible only to the one civilization it is aimed at. To everyone else, it is a flare with a bearing on it. There is a second correction to make, and it changes the emotional shape of this entry considerably. It is the same correction that closed the previous item, and it is worth sharpening rather than repeating. The version of this fear that circulates assumes we have already given ourselves away. 125 years of radio, spreading outward, arriving at one star after another. As established, that is largely false. Leakage falls below the natural radio noise of the galaxy almost immediately. Nobody is watching our television. What is actually detectable about this planet is not what we transmit. It is what we have done to the air. Ravi Kopparapu and colleagues showed in 2021 that industrial nitrogen dioxide could serve as a technosignature, detectable in the spectrum of a temperate planet out to roughly 30 light-years with a sufficiently large future telescope. Nitrogen dioxide has natural sources, but not at industrial concentrations. Jacob Hack-Misra and colleagues argued in 2022 that chlorofluorocarbons, molecules with no natural source whatsoever, which exist only because chemists made them, would be within reach of the James Webb Space Telescope for a planet in a system like TRAPPIST-1. And carbon dioxide has risen from about 280 parts per million before 1750 to over 420 parts per million now, a change that is visible in the atmosphere's absorption spectrum and has been building for 2 centuries. So if anyone in this galaxy is reading planets rather than listening for broadcasts, and reading planets is by far the more sensible method, since a planet is always there and a broadcast is not, then the signature is chemical. It is unambiguous. It does not switch off, and it has been accumulating since long before anyone alive was born. The debate about whether to send a message is, on that reading, somewhat beside the point. The message that matters was never a message. And finally, the distinction that earns this entry its place on a countdown about the dead, because there are 2 versions of this theory, and they describe completely different galaxies. In one version, civilizations are hiding. They detected the logic, drew the conclusion, went quiet, and are still out there, a galaxy full of survivors, each of them silent by choice, each of them alive. The silence is a decision. In the other version, the hunters have already done their work, repeatedly, for billions of years, and what remains remains. The silence is a result. Nothing we can currently measure distinguishes those 2 galaxies. They produce identical observations, no signals, no megastructures, no visitors. And unlike every entry above this one, there is no instrument that could be built to settle it, because the prediction of both versions is the same absence. There is an institutional asymmetry here that says something about how seriously the field takes its own argument. The community has developed detailed post-detection protocols and a scale for rating the significance of a candidate signal, all of it governing what to do if we hear something. There is no equivalent binding agreement governing what may be transmitted. Listening has procedures. Speaking does not. Whether that reflects confidence or oversight is left as an exercise. And the one candidate signal that has never gone away is worth naming, because it is the reason the listening continues. On the 15th of August 1977, the Big Ear radio telescope in Ohio recorded a narrow-band burst 30 times stronger than the background, lasting 72 seconds, at almost exactly the frequency at which neutral hydrogen radiates. Jerry Amon, reviewing the printout days later, circled the readings and wrote a single word in the margin. It has never repeated, despite many searches with better instruments, and no natural explanation has been established. It is one detection, unconfirmed, from an era of much cruder equipment, and it has occupied the field for nearly 50 years, which tells you how thin the evidence in this area actually is. So, have we looked? We have listened, continuously, for 65 years, across widening bands of the spectrum, and heard nothing that repeated. But this entry does not really predict a detection. It predicts the absence of one, which is exactly what we have, which is why it can never be confirmed and can never be ruled out. There is one more asymmetry worth carrying forward. Of the two versions, the hiding version is the one that requires every civilization to have reached the same conclusion and acted on it consistently for millions of years. The hunted version requires only that somebody, once, decided differently. Brin's original observation applies to the theory's own internal structure. The frightening reading is the one that needs fewer assumptions, and needing fewer assumptions is not the same as being true. But the next theory says none of that ever mattered, because most worlds never get far enough to be worth hiding from. Number 5. The world that never learned to burn. We are halfway down, so it is worth stopping for a moment and noticing what has happened to the evidence. We began with atoms. Physical atoms, in a jar, drilled out of the Pacific floor and melted out of Antarctic snow and carried back from the surface of the moon. Then we move to an event that leaves no chemical trace at all and can only be inferred from a pattern of who died. Then to machines that ought to be sitting in this solar system and are not, as far as several deliberate searches can tell. Then to an archive supposedly written into the genome, which we have finally finished reading and do not yet understand. And then to an argument about strategy that predicts no evidence whatsoever and cannot, even in principle, be checked. 5 entries, and we have gone from a jar of atoms to an argument about air. That descent is the structure of this list, and the second half continues it. Which brings us to the coldest theory here, because it does not require anything to have killed anyone. Peter Ward, a paleontologist, and Donald Brownlee, an astronomer, both at the University of Washington, published the argument in book form in the year 2000 under the title Rare Earth. And their claim is misquoted so consistently that it is worth stating precisely before examining it. They did not argue that life is rare. They argued the opposite, that microbial life is probably common, possibly abundant, quite likely present on multiple bodies in this solar system. What they argued is rare, is complex, multicellular, animal-grade life, the kind that can build a nervous system, and eventually a telescope. Their case is that this second stage requires a stack of planetary conditions so specific and so mutually dependent that most of the universe never assembles them. On that reading, the galaxy is not a graveyard at all. It is a swamp, enormously alive and permanently quiet. Let us go through the stack, because each piece is a real result, and several of them have been substantially revised since the book was written. First, a galactic habitable zone. Far enough from the crowded inner galaxy to avoid the frequent sterilization events we discussed at the top of this list, and close enough in that there are sufficient heavy elements to build a rocky planet at all. Those two constraints pull in opposite directions, which is what makes it a zone rather than a limit. Charles Lineweaver, Yeshe Fenner, and Brad Gibson quantified it in the journal Science in 2004 and estimated that roughly 10% of Milky Way stars qualify, concentrated in an annulus, and biased towards stars that formed between 4 and 8 billion years ago. That figure has been contested repeatedly and revised in both directions ever since, and it should be held as one modeled number rather than a measurement of anything. Second, a stable star, and preferably a single one. Massive stars burn out in millions of years, which is not enough time for the processes we are about to discuss. That excludes the brightest stars in the sky and leaves the quiet ones. The book also leaned on a figure that has since changed. The old textbook claimed that roughly half of all stars are in multiple systems, which would sharply restrict the number of stable, long-lived orbits available. Charles Leder pointed out in 2006 that this figure came from surveys biased toward bright, massive stars. Because the overwhelming majority of stars in this galaxy are small red ones, and because small red ones are usually single, the majority of stellar systems are in fact single. That is a correction in the optimistic direction, and it is worth registering that the revisions to this argument have not all gone one way. There is another number worth putting alongside it. The Kepler mission's occurrence rate analyses suggest that something like 1 in 5 Sun-like stars hosts a roughly Earth-sized planet at a temperate distance. The published ranges around that figure are wide, and the word temperate is doing an enormous amount of work. It usually means only that liquid water could exist somewhere on the surface, given a suitable atmosphere, which is a much weaker statement than it sounds. But even the pessimistic end of that range implies billions of candidate worlds in this galaxy alone. The rare Earth argument is not disputing that number. It is arguing that the number is nearly irrelevant, because the filter it proposes operates after a planet is already in the right place. Third, and this is the single most repeated claim in the whole rare Earth literature, a large moon. Jacques Lascar and colleagues published a calculation in Nature in 1993, showing that without the moon, Earth's axial tilt would wander chaotically across a range approaching 0 to 85 degrees. An 85-degree tilt means the poles point almost directly at the sun in turn. It means each hemisphere spends half the year in continuous daylight and half in continuous darkness, with climate swings no complex ecosystem could track. That claim has been substantially softened, and the softening deserves the same airtime the original got. Jack Lissauer, Jason Barnes, and John Chambers revisited the calculation in the journal Icarus in 2012 with better numerical methods and longer integrations. Their result was that the excursions for a moonless Earth are more like 10 to 50 degrees over tens of millions of years. Still large. Still consequential for climate. Not the catastrophe the popular version describes. And it is worth adding that the moon is receding, measured by bouncing lasers off the retroreflectors left by the Apollo 11, 14, and 15 crews. It moves away at about 3.8 centimeters a year, roughly the rate at which fingernails grow. So, whatever stabilizing effect it provides is slowly weakening anyway. Fourth, a gas giant in the right orbit. George Wetherill argued in 1994 that without Jupiter, the flux of long-period comets into the inner solar system would be higher by a factor approaching 1,000. The dinosaurs were ended by one impact. The image of 1,000 times that rate is a powerful one, and it appears in nearly every popular treatment of this subject. Jonathan Horner and Barry Jones spent several years in the late 2000s testing the claim by direct simulation, running the solar system with the giant planet's mass varied across a wide range. Their finding was that the picture is considerably more complicated. A Jupiter mass planet is roughly optimal as a shield. But at intermediate masses, around the mass of Saturn, for instance, a giant planet actually increases the impact rate because it is efficient at perturbing objects onto inward crossing orbits without being massive enough to eject them from the system entirely. Jupiter is a shield and a slingshot at the same time, and which one dominates depends on the population of small bodies you are asking about. The thousandfold figure is not the settled answer it is usually presented as. Fifth, plate tectonics, which drives the mechanism that has actually kept this planet alive. James Walker, Paul Hayes, and James Casting described it in 1981, and it is one of the more elegant feedback loops in nature. Warming increases rainfall. Rainfall increases the chemical weathering of exposed silicate rock. Weathering consumes carbon dioxide and locks it into carbonate minerals, which are eventually carried into the mantle at subduction zones. Less carbon dioxide means cooling. The loop runs the other way too. Cooling reduces weathering, volcanic carbon dioxide accumulates, and the planet warms back up. The response time is around 500,000 years, which is slow by any human measure and fast by geological ones. And it has been necessary because the sun has not been constant. Carl Sagan and George Mullen pointed out in 1972 that the early sun was only about 70% as bright as it is today. By straightforward calculation, the young Earth should have been frozen solid. It was not. There is liquid water in the rock record from very early on. The thermostat is the leading explanation for how a planet stayed in the same narrow temperature band while its heat source brightened by 30% over 4 billion years. The thermostat is not infallible, and the record shows it failing. Around 717 million years ago, and again around 650 million, this planet froze from the poles to somewhere near the equator, in episodes usually called Snowball Earth. Ice reflects sunlight, so once the ice advances past a certain latitude, the cooling accelerates itself, and the planet locks. What eventually released it was the same thermostat running in reverse, with the oceans covered and weathering essentially stopped. Volcanic carbon dioxide accumulated in the atmosphere for millions of years until the greenhouse effect overwhelmed the ice. The recovery is the reassuring part of that story. The fact that it happened at all, twice, on a planet with every condition on this list satisfied, is not. And there is a sixth item that Ward and Brownlee dwell on and that later work has sharpened considerably. Complex cells appear to have arisen exactly once. Every plant, animal, fungus, and alga on this planet descends from a single event in which one simple cell ended up inside another, and the two did not separate. That event produced mitochondria, and mitochondria are the reason large genomes are possible. Nick Lane's argument for why this is a genuine bottleneck rather than an accident of survivorship is energetic and concrete. A simple cell has, on the order of tens of thousands of times less energy available per gene than a complex one, because it must generate power across its outer membrane, and that membrane's area does not scale usefully with size. Mitochondria removed that ceiling by putting power generation inside, in structures that can be multiplied at will. Without that arrangement, a cell can be efficient, and it cannot be large or complicated. And in 4 billion years of experimentation across every environment this planet offers, it happened once. The delay that followed is its own piece of evidence. Oxygen rose 2.4 billion years ago. The Cambrian explosion, the sudden appearance of most major animal body plans in the fossil record, begins around 538.8 million years ago. That is a gap of nearly 2 billion years between the availability of the fuel and the arrival of the animals. Something was gating that transition for a span of time longer than the age of most of the objects in the night sky, and working out what is one of the more consequential open problems in the earth sciences. And then there is the condition almost nobody includes, which is the reason this entry belongs on a list about civilizations rather than on a list about biology. At the very end of 2023, Amedeo Balbi and Adam Frank published a short paper in Nature Astronomy setting out what they called the oxygen bottleneck. The argument is simple enough to state in one sentence and large enough to reorganize the whole question. Technology, as distinct from intelligence, depends on open-air combustion. Consider what fire actually does for a species. It cooks, which unlocks calories. It fires clay, which gives you containers and construction. It smelts ore, which gives you metal. Metal gives you tools that make better tools, and a furnace hot enough to work iron is the beginning of every industrial process that follows. Chemistry, glass, ceramics, engines, electricity generation, the entire chain that leads from a stone tool to a radio telescope runs through controlled burning at some point, and most of it runs through burning at nearly every point. And sustained open-air combustion has a hard requirement. It needs atmospheric oxygen of at least roughly 18% by volume. Below that threshold, a flame will not propagate reliably through fuel in open air. It will not sustain. You can have a spark, and you cannot have a fire. Earth's atmosphere is about 21% oxygen, comfortably above the line. But it has not always been. The Great Oxidation Event, around 2.4 billion years ago, took atmospheric oxygen from essentially nothing to perhaps a few percent, a transformation driven by cyanobacteria and one of the largest changes this planet has ever undergone. And then it stalled. Oxygen stayed low for well over 1 billion years, a period sometimes called the boring billion, and it did not approach modern levels until much later. The direct physical evidence for when fire became possible is charcoal. Charcoal is the residue of a wildfire. It preserves well, and it is unambiguous. The charcoal record on this planet begins in the Silurian, roughly 420 million years ago. Before that, the rocks record no fires, because there were none to record. Sit with what that means. Life has existed here for something close to 4 billion years. For roughly 90% of that span, a species could have been as intelligent as it liked, as social, as dexterous, as communicative, and could not have lit a fire. Not through lack of ingenuity, through lack of an oxidizer, which reframes the entire question this video has been asking. A planet can produce a nervous system. It can produce social organization, language, abstraction, planning, even tool use of the kind we see in crows and octopuses and primates. And it can stop there permanently, not because of any barrier in the mind, but because of the composition of the air. Such a world would be permanently pre-industrial. Not primitive, pre-industrial, which is a different and much more interesting thing. There would be no radio from it, no waste heat, no atmospheric technosignature, nothing detectable at any distance by any method we possess or can currently imagine. From here it would be indistinguishable from a bare rock. Balby and Frank's practical recommendation is modest. Oxygen abundance should be treated as a prior when planning searches for technological signatures, because a world below the threshold cannot produce them regardless of what lives there. It is a small suggestion carrying a very large implication, which is that a substantial fraction of the inhabited worlds in this galaxy may be inhabited by something that will never make a sound. Titan is the nearby illustration. Saturn's largest moon has lakes of liquid methane, a thick atmosphere, and complex organic chemistry falling out of the sky as haze. It is drenched in fuel. It has no free oxygen at all, so none of that fuel can burn. Whatever Titan is, it is a world where combustion is chemically forbidden, and it has been that way for 4 billion years. The opposite failure is also possible. Above roughly 35% oxygen, fires do not stop once started. Even damp vegetation will carry a flame, and a lightning strike propagates until it runs out of fuel or reaches water. The Carboniferous period, at perhaps 31% oxygen, is the closest this planet has come, and the fossil record from that period is full of charcoal. There is a habitable band for technology as well as for life, and it is narrower than the one for water. Now the counterweight, and it is a strong one, because this is not a settled question. In February of 2025, Dan Mills, Jennifer McAlady, Adam Frank and Jason Wright published a reassessment in Science Advances that attacks the logic underneath the whole rare earth framework. Their argument is that the major transitions in Earth's history look improbable only if you assume the planet was a suitable venue for them throughout its history. It was not. Oxygenation, nutrient availability, ocean chemistry, and global temperature each opened windows in sequence, and when you line up each transition against the window that permitted it, each one occurred reasonably promptly once its window opened. On that reading, humans did not squeak through a series of lottery draws that most planets lose. We arrived roughly on schedule for the planet we happen to live on, and the long delays in our history measure how long it took the Earth to become ready, rather than how unlikely we were. The rare Earth argument and this reassessment cannot both be fully correct. One says the conditions are a stack of coincidences. The other says the conditions are a sequence, and that sequence is complete. The honest position, and the one this video is going to take, is that the question is open, that it is being actively worked on, and that it will not be settled by argument. It will be settled by taking spectra of a large number of temperate rocky planets and finding out how many of them have oxygen in the air. So, have we looked? Not yet, not properly. We can detect atmospheres on large planets and on small ones around small stars, and we are only beginning to reach the case that matters. The instruments that would answer this are being built now, and we will come back to them at the end of the list. The next theory returns to worlds that did learn to burn, and it argues that learning to burn is exactly what kills them. Number 4. The 100-year window. There is a gap in the life of any technological species, and the argument of this entry is that the gap is short. So on one side of it, you are detectable. You have radio. You have industry. You have changed the composition of your own atmosphere in ways that are visible from other star systems. On the other side of it, you are durable. You exist on more than one world, with independent food production, independent power, independent manufacturing, so that no single event on any single planet can end you. The distance between those 2 points, measured in years, is the number that decides whether a galaxy fills up or empties out. And for one species, on one planet, we can measure it directly because we are standing in the middle of it. The first edge is well dated. Heinrich Hertz demonstrated the existence of radio waves in his laboratory in 1887, confirming a prediction James Clerk Maxwell had made on paper 2 decades earlier. Guglielmo Marconi sent a signal across the Atlantic in December of 1901. Commercial broadcasting began in the 1920s. Within about 40 years of the first laboratory demonstration, the technology was ordinary. The second edge has not arrived. There is no self-sustaining human settlement anywhere except this planet, and no credible near-term schedule for one that does not depend on continuous resupply from Earth. Every human being who has ever lived has lived within a few hundred kilometers of the surface of one world. And between those 2 edges, within a single human lifetime, the other thing arrived. The first nuclear detonation took place in the New Mexico desert on the 16th of July, 1945. That is 58 years after Hertz. This is the part of the argument that does not depend on anything about human nature, and it is worth stating carefully because it is the strongest version of the claim. Radio and fission are not independent inventions that happened to occur close together by cultural accident. They are consequences of the same body of physics, understood in the same half-century by the same institutions, often by the same people. You cannot reach one without passing very near the other. Maxwell's equations and the structure of the atom are neighbors in the logical order of discovery, and any species that works its way through that territory will encounter both, roughly together. Physics is the same everywhere. What varies is who is holding it. The formal home of this argument is the last term of an equation written on a blackboard in November of 1961. The place was Green Bank, West Virginia, and the occasion was a 3-day meeting attended by 10 people. Frank Drake, who had run the first modern search for radio signals from other stars the year before. Carl Sagan, then in his 20s. Otto Struve, one of the most distinguished astronomers of the century. Philip Morrison, who had co-authored the paper that started the field. Melvin Calvin, who learned during the meeting that he had won the Nobel Prize in Chemistry, which is the kind of detail that makes a historical moment feel like a real afternoon. They later called themselves the Order of the Dolphin, after a member's work on dolphin communication. Drake wrote 7 terms on the board. He has said many times since that he intended them as an agenda, a way of organizing 3 days of discussion into topics, rather than as a theory. Multiply them together, and you get an estimate of how many civilizations in this galaxy are currently transmitting. 6 of those 7 terms have improved enormously in the 65 years since. We know the star formation rate. We know, thanks to Kepler and its successors, that planets are common, and roughly how common temperate rocky ones are. The biological terms are still uncertain, but the uncertainty is now bounded by real data about early life, extremophiles, and the chemistry of the outer solar system. The 7th term is exactly where they left it. That term is the average lifetime of a communicating civilization. Not the lifetime of a species, the length of time it spends being detectable. And it has not improved at all in 65 years of extraordinary progress in every adjacent field, for a reason that no funding and no instrument can fix. There is one data point. It is us, and it is not finished. That is the weight of this entry, and it is worth sitting with. 10 people spent 3 days in a room in West Virginia, wrote down a question about their own survival, and handed it forward unanswered. Everyone in that room is now gone. The question is still open. It is still ours. And the last term dominates the result. This is not a rhetorical point, but an arithmetic one. If the average communicating lifetime is 100 years, against a galaxy 13.6 billion years old, then at any given instant, the fraction of all civilizations that have ever existed which are currently transmitting is roughly 1 in 136 million. You could have a galaxy that produced 100,000 civilizations over its history and expect, right now, to be able to hear precisely none of them. The silence would not indicate rarity. It would indicate brevity. There is an inversion of the same arithmetic that is worth putting beside it, because it cuts the other way, and it is one of the more elegant results in this field. In 2016, Adam Frank and Woodruff Sullivan published a paper in the journal Astrobiology, which set aside the lifetime question entirely and asked a different one, not how many civilizations exist now, but how many have ever existed. That question removes the term nobody can measure, because a civilization that lasted a century and ended 1 billion years ago still counts. Working from the known number of habitable zone planets, they calculated what the probability per planet would have to be for humanity to be the only technological species that has ever arisen anywhere in the observable universe. The answer was below roughly 1 in 10 to the 22nd. To put that in some kind of proportion, it is a probability smaller than picking one specific grain of sand from every beach and desert on Earth, several times over. Their point was not that we are definitely not alone. It was that the claim of being alone is itself an extraordinary claim, requiring an extraordinarily small number, and that most people asserting it have not noticed how small. So the pessimistic reading and the optimistic reading converge on the same picture. A great many civilizations have probably existed. Almost none of them are currently detectable. The difference between those two statements is the seventh term. Carl Sagan's phrase for the stage a species occupies inside the window was technological adolescence, the interval between acquiring capabilities that can end you and acquiring the maturity to manage them. He framed the seventh term explicitly as a question about whether adolescence is survivable, not about whether it is common. And he was careful to point out that the answer, whatever it is the same for everyone, because the physics is the same for everyone. The scale of what has been built inside our own window is worth stating plainly and calmly, because the numbers are not in dispute. The global nuclear stockpile peaked at roughly 70,300 warheads in 1986. It stands today at something over 12,000, a reduction of more than 80%, which is a genuine achievement and still leaves an arsenal several times larger than anything that could be described as sufficient. In 1983, 5 researchers, Richard Turco, Owen Toon, Thomas Ackerman, James Pollock, and Carl Sagan, published the first climate modeling of what happens when large quantities of soot from burning cities are injected into the stratosphere. Their conclusion, that the resulting cooling and darkness would be more lethal than the detonations themselves, introduced a phrase into the language. The Bulletin of the Atomic Scientists has published a symbolic clock since 1947. In January of 2025, it was set to 89 seconds before midnight, the closest position in its history. One further feature of that period deserves attention, because it is the detail that makes the seventh term feel less like a statistic. The closest approaches were not the product of policy debated over decades. They were the product of decisions made in minutes by small numbers of individuals under bad information. In October of 1962, during the Cuban crisis, a Soviet submarine under depth charge attack and out of radio contact came within one officer's refusal of launching a nuclear torpedo. In September of 1983, a Soviet early warning system reported incoming missiles, and the duty officer, Stanislav Petrov, judged it a malfunction and did not pass the report up the chain. It was a malfunction, sunlight reflecting off high cloud. Whatever the seventh term turns out to be for this species, part of its value was set on those 2 occasions by 2 people whose names very few people know. That is not a comfortable way for a civilization's lifetime to be determined, and there is no obvious reason to think other civilizations arrange things better. 2 recent peer-reviewed arguments extend the mechanism well beyond weapons, and both are worth taking seriously. In 2024, in the journal Science Progress, Olev Vin published an argument about inherited behavior patterns. The reasoning runs as follows. Intelligent social organisms arrive at civilization carrying traits shaped by millions of years of natural selection under conditions of scarcity, small group size, and immediate physical threat. Competition for status. Accumulation of resources beyond need. Strong preference for the in-group and suspicion of outsiders. Those traits were adaptive. They are the reason the lineage survived long enough to build anything. And they are structurally mismatched to the conditions a technological civilization creates, in which the group is planetary, the resources are shared, the timescales are long, and the consequences of competition are global. The unsettling part of that argument is not the pessimism. It is the generality. If it holds, the danger is not a wrong decision that a wiser species might avoid. It is a design constraint. Any species that arrives at technology by natural selection arrives carrying the traits that natural selection used to get it there, and those are the traits that destabilize what it built. In the same year, in the journal Acta Astronautica, Michael Garrett, who holds the Sir Bernard Lovell Chair of Astrophysics at Manchester, asked whether artificial intelligence is the filter. His argument has 3 parts. that the development of highly capable artificial intelligence is plausibly a convergent step for any technological civilization, that it arrives quickly relative to the time required to become multiplanetary, and that it could therefore cap the communicative lifetime at something on the order of 1 to 200 years. What is unusual about that paper is its ending. Most work in this literature concludes with a call for more observation. Garrett's concludes with a deadline. If the reasoning holds, then establishing an independent presence beyond one planet is not an aspiration or a preference. It is a race against a clock whose length we do not know. It is worth naming the other candidates briefly, because the argument does not stand or fall on any one of them. Engineered pathogens are the hazard with the lowest barrier to entry. The cost of synthesizing genetic material has fallen faster over the last 2 decades than any governance framework has adapted, and unlike a weapons program, the equipment fits in a room. Climate change operates on a slower schedule and is not, on any mainstream projection, an extinction mechanism, but it is a stress multiplier that makes every other failure more likely. And there is the category of things nobody has thought of, which historically has been the largest category. The point of the argument is not to rank these. It is that the window has one entrance and many exits, and that a species only has to fail once. It is equally worth being precise about how far away the far edge of the window actually is, because public conversation tends to treat it as nearly reached. A self-sufficient off-world settlement is not a base with a resupply schedule. It is a complete industrial civilization, mining, refining, chemical processing, semiconductor fabrication, pharmaceutical manufacture, agriculture, and the ability to replace every machine involved in all of those when it breaks. Estimates for the population required run into the tens or hundreds of thousands, together with a supply chain that on this planet spans continents. Nothing resembling that exists or is under construction. The near edge of the window was crossed in 1901. The far edge is not in sight. Stephen Hawking spent much of his final decade arguing that the far edge would not be reached in time by an unmodified species, and that biological or computational augmentation was therefore a prerequisite rather than an enhancement. It belongs here as a named position held by a serious person, and it is worth noting that it is a position about the 7th term rather than about technology. He was arguing about how long we have, not about what we could build. Now the question this list keeps asking, and the reason this entry sits at number 4 rather than higher. What would a civilization that ended this way leave behind? On its own world, a great deal. There would be a layer in the sedimentary record, unlike anything below it. Plutonium isotopes from atmospheric testing, fly ash from combustion, concrete, aluminium, plastics that no natural process produces, and few natural processes break down. That layer will be legible in the rocks of this planet for millions of years. Anyone standing on the surface with a geologist's hammer would find it immediately. It is worth describing that layer properly, because it is the most durable thing this species has made. It contains plutonium isotopes that exist nowhere in nature at these concentrations, deposited globally by atmospheric testing between the 1950s and the early 1960s, with a sharp onset and a sharp decline that marks a period of about 15 years with a precision no other geological boundary can match. It contains spherical fly ash particles from coal combustion, which are chemically distinctive and physically unmistakable. It contains concrete, which is the second most used substance on the planet after water, and aluminium, which does not occur in metallic form naturally at all. It contains plastics, in quantities now measurable in ocean sediment worldwide. And it contains a bone layer, the remains of domesticated chickens, which are the most numerous bird in the history of the planet by a very wide margin, and whose skeletons are morphologically unlike any wild ancestor. A geologist arriving on this planet 50 million years from now would find that layer in the first afternoon, would recognize it as anomalous within minutes, and would be able to determine a great deal about what made it. The record is excellent. The problem is entirely one of range. From 40 light-years away, none of that is readable. We cannot resolve surface features on any exoplanet, and will not be able to for a very long time. What might in principle be detectable is atmospheric, the residue of an industrial phase written into a spectrum, or the chemical aftermath of a large-scale exchange. Adam Stevens, Duncan Forgan and Jack O'Malley James examined exactly this in 2016 in a paper on the observational signatures of self-destructive civilizations, and their conclusion is the quiet center of this entry. Most of the signatures decay. Atmospheres self-repair. Biospheres reassert themselves. The weathering cycle we discussed at number 5 keeps running whether or not anyone is there to benefit from it. Picture the result. A temperate world, 300,000 years after its civilization ended. 300,000 years is nothing, a 15,000th of the age of the planet, roughly the interval since anatomically modern humans first appeared. The atmosphere has already scrubbed itself. Carbon dioxide has returned to its pre-industrial baseline through ordinary silicate weathering. The nitrogen dioxide is long gone, because nitrogen dioxide has a residence time measured in days. The chlorofluorocarbons have been broken apart by ultraviolet light. Whatever grows there has grown over the sites, and the sites themselves are compressed into a centimeter of unusual sediment somewhere below the root layer. And from a telescope 40 light-years off, pointed at that world with the best instrument anyone could build, the spectrum is clean. Water, oxygen, nitrogen. A temperate, living, entirely unremarkable planet, well within the range that would make it a priority target. There is no line in that spectrum for what happened. There is no way to ask. That is the shape of this entry. The readable portion of a civilization's existence expires far faster than the planet does, and, on the argument above, roughly as fast as the window that ended it. So, have we looked? We are looking now, and we are looking at the wrong thing, through no fault of anyone. We search for signals, which requires the transmitter to be running at the moment we happen to point at it. The thing that would actually survive, the atmospheric residue, fades within a few 100,000 years, which sounds enormous and is a rounding error against the age of the galaxy. Even if this theory is exactly right, and even if it has happened 10,000 times in this galaxy, the number of those events still visible today would be small enough to have been missed by every survey ever run. And there is one more thing that separates this entry from every other theory on the list, which is worth naming before we move on. Every other item here is a claim about somewhere else. Supernovae happened near other stars. Machines were built by someone else. The codes were written by someone else. This one is a claim about here, about now, and about a measurement that is currently being taken. Whatever the 7th term turns out to be, its value for this species is being determined during the lifetime of everyone listening to this by a very large number of ordinary decisions, most of which will never be recorded. That is not offered as a warning. It is simply what the theory says, stated accurately. The experiment is running. The sample size is 1. The next theory keeps the window and removes the ending. On that theory, nobody dies at all. They simply stop being visible, and they do it on schedule. Number 3, the ones who went inward. Every theory above this point assumes that a civilization which stops transmitting has stopped existing. This one proposes the opposite. On this account, they are entirely fine, and we cannot see them because advanced civilizations do not expand outward at all. John Smart published the argument in Acta Astronautica, volume 78, pages 55 to 68 in 2012. Its core is a claim about the direction of technological progress, which he calls STEM compression, compression of space, time, energy, and matter. The observation underneath it is that leading-edge systems become denser, faster, more energy efficient, and physically smaller per unit of computation, generation after generation, and that this trend has been far more consistent historically than any trend toward physical expansion. The evidence for the trend is our own, and the comparison is stark enough to be worth setting out precisely. The Intel 4004, released in 1971, had a feature size of 10 micrometers and contained 2,300 transistors. Current logic processes are labeled at a few nanometers and place tens of billions of transistors on a single die. That is roughly 9 orders of magnitude of improvement in density in about half a century, a factor of 1 billion. Over the same period, the furthest human artifact is Voyager 1, launched on the 5th of September 1977. It has traveled about 170 times the distance from the Earth to the Sun. That sounds like a great deal, and it is the furthest anything made by human hands has ever gone. It is also roughly 1/6000th of the way to the nearest star. One curve went 9 orders of magnitude. The other did not go one. Smart's argument is that if this asymmetry is general, rather than a local accident of our particular history, then the observable behavior of an advanced civilization is not colonization. It is disappearance. It is worth extending that comparison backwards because the shape of the curve is the whole argument. The first general-purpose electronic computer, completed in 1945, occupied about 167 square meters of floor space, weighed 27 tons, contained around 17,000 vacuum tubes, and drew 150 kilowatts. It could perform a few thousand additions per second. A modern telephone performs more arithmetic in a second than that machine performed in its entire operational lifetime, fits in a pocket, and runs on a battery the size of a playing card. 80 years separates them. Now extrapolate that curve forward by even 1,000 years, not 1,000,000, not 1,000,000,000, 1,000, and the endpoint is not a bigger computer. It is something operating at scales where the ordinary vocabulary of engineering stops applying. Smart's argument is that this is the actual trajectory of a technological civilization, and that everything we imagine advanced civilizations doing, building structures around stars, spreading across the galaxy, transmitting across the void, is a projection of 19th century industrial expansion onto a process that does not work that way. The idea has a respectable precursor. John Barrow proposed in 1998 an inward-facing counterpart to the standard scale of civilizations, which classifies by the amount of energy commanded. Barrow's version classifies instead by the smallest scale of matter a civilization can manipulate, from bulk objects to mechanisms, to molecules, to atoms, to atomic nuclei, to elementary particles, to the structure of space itself. On that scale, the technological history of this species is a fairly steady descent, and it has been descending faster in the last century than in all the preceding ones combined. The physics that makes the destination specific rather than vague comes from thermodynamics and gravity, and it is a genuinely elegant chain. Rolf Landauer showed in 1961 that erasing one bit of information necessarily dissipates at least a certain minimum energy, about 2.87 zeptojoules at room temperature, which is a quantity so small it took 50 years to measure. Antoine Beru, Eric Lutz and colleagues confirmed it experimentally in Lyon in 2012, using a single microscopic bead, in an optical trap. The important feature of Landauer's result for this argument is that the minimum scales with temperature. Computation in a cold environment is fundamentally cheaper than computation in a warm one. Not marginally cheaper, cheaper as a matter of physical law. Seth Lloyd worked out the other end of the scale in the year 2000, calculating the ultimate physical limits of computation for a kilogram of matter occupying a liter of volume. The answer was about 10 to the 51st operations per second on 10 to the 31st bits. For comparison, a fast modern processor performs something like 10 to the 11th operations per second. The gap between what we build and what physics permits is around 40 orders of magnitude. And the configuration that achieves the limit is not a machine in any recognizable sense. It requires the matter to be converted into a plasma at roughly 1 billion Kelvin, at which point the distinction between a computer and an exotic astrophysical object stops being meaningful. Then Jacob Bekenstein and Stephen Hawking established, in the early 1970s, something stranger still. The maximum amount of information that can be contained within a region of space is proportional not to the volume of that region, but to the area of its boundary. That is deeply counterintuitive. It means a sphere twice as wide holds 4 times as much information, rather than 8 times. And the object that saturates the bound, holding the theoretical maximum, is a black hole. Add gravitational time dilation, and the argument arrives at its destination. Close to a horizon, a process running at some rate locally appears vastly slower when measured from far away. Inverted, that means a system positioned near a horizon can complete an enormous amount of internal processing during a modest interval of outside time. Smart's proposal is that a civilization following the compression gradient far enough ends at a black hole-like destination, which is, by the construction of the physics itself, censored from external observation. It does not stop existing. It stops emitting. 2 details make the destination more concrete, and both are worth a moment. The first is how much room there actually is. Apply the information bound to a volume the size of a human being, and the theoretical capacity comes out at something like 10 to the 70th bits. The information content of a human body, described at the level of atoms and their arrangements, is a vanishingly small fraction of that. Which means that in terms of the physical limits on information density, biology has not begun to compress. We are, in the strictest sense the physics permits, almost entirely empty space with a few instructions in it. The second is durability. A black hole is not a temporary structure. Hawking radiation causes them to evaporate, but the timescale for a hole of stellar mass is around 10 to the 67th years, a duration against which the current age of the universe, 13.8 billion years, is indistinguishable from zero. Whatever else can be said about that destination, it is stable for any purpose a civilization could conceivably have. Every star will have burned out, and every ordinary structure will have dispersed long before it changes. There is also a cost that the popular version of this idea usually omits. Benefiting from time dilation near a horizon requires staying near the horizon, and staying near a horizon means fighting gravity continuously. The energy budget for holding a structure in place close to a black hole is severe, and it is not obvious that the computational gain outweighs it. That is the kind of engineering objection that does not refute a hypothesis and does considerably complicate it. The honest limits have to be stated clearly, because this is the most speculative entry above number 1, and the temptation to present it as established is real. Nobody has a working account of how information could be retrieved from inside a horizon. The black hole information problem, raised by Hawking in 1976, asks whether information that falls in is destroyed, which would violate a foundational principle of quantum mechanics, or preserved in some form. The calculations published from 2019 onward, involving the entropy curve of an evaporating hole and the geometry of entanglement, suggest strongly that information is preserved. Suggesting is not the same as showing how anything inside could use it. More broadly, SMART's proposal is a developmental argument built on an extrapolated trend, and extrapolated trends have a poor record over long timescales. The trend he relies on is 50 years long. He is applying it across billions. And there is a serious counter-argument from an equally serious source. Freeman Dyson made precisely the opposite case in a paper called Time Without End in 1979. His argument was that the survival strategy for intelligence in an expanding, cooling universe is to spread out rather than concentrate, to reduce the rate of thought to match the falling temperature, and to hibernate for increasingly long intervals, buying an unbounded amount of subjective experience out of a finite energy budget. Outward and thinner, not inward and denser. Both cannot be the universal attractor for advanced intelligence, and there is no way at present to determine which, if either, is right. There is also a straightforward objection from our own behavior. We did both. We miniaturized transistors by a factor of 1 billion, and we also launched Voyager. A civilization can pursue two strategies at once, and this hypothesis requires the inward one to win completely and everywhere, which is a strong requirement for a species that has been doing both for 50 years. A further complication is worth mentioning because it is happening now. Computation is getting cheaper per operation and simultaneously more expensive in aggregate. Data center electricity demand has grown steadily even as individual operations became more efficient, which is the classic pattern of a resource becoming cheap enough that consumption expands to fill the saving. That is not what pure compression looks like. It is what compression plus growth looks like, and growth needs space. There is one argument in favor of compression that deserves more weight than it usually receives, and it has nothing to do with efficiency. It has to do with latency. Any system that thinks is limited by the speed at which its parts can communicate, and no signal travels faster than light. A structure the size of a solar system has an internal communication delay, measured in hours. A structure the size of a galaxy has one measured in tens of thousands of years. If a civilization becomes, in any meaningful sense, a single thinking thing, then expanding it does not make it more capable. It makes it slower, and eventually it makes it several separate things that cannot coordinate. Beyond a certain size, growth is not growth. It is division. Compression has the opposite property. Everything gets closer together, so everything gets faster. If the value a civilization cares about is the richness of what it experiences rather than the volume of space it occupies, then the physics points inward, unambiguously, and it keeps pointing inward all the way down. That is the strongest form of SMART's argument, and it does not depend on any trend line at all. It depends only on the speed of light being finite. SMART uses the phrase developmental singularity for the endpoint, a term chosen carefully, because developmental means the process is the ordinary maturation of a system rather than an accident or a catastrophe. On this account, a civilization arriving at that destination has not failed and has not been destroyed. It has grown up, in the way an embryo grows up, along a path that was implicit in the physics from the beginning. So what earns this entry its place on an evidence-ranked countdown? This is the part that separates it from most proposals in this area. SMART's version makes a prediction with a shape. If transcension is what advanced civilizations do, then the oldest habitable systems should be the quietest. The inner reaches of the galactic habitable zone, where planet formation began earliest, where heavy elements accumulated first, where any civilization would have had the largest head start, should be conspicuously empty of techno-signatures relative to their age. Smart called this a missing planets problem, not the absence of planets, but the absence of activity precisely where the odds most favor it. That is a statistical prediction about an absence, which is a difficult thing to test and is not the same as untestable. As surveys of nearby systems approach completeness, the age distribution of quiet systems becomes a real, measurable number. If quiet correlates with age, that is a data point. If it does not, the hypothesis has a problem. There is a second implication, and it is unusually specific for a theory in this field. If civilizations compress inward on a timescale of a few thousand years after reaching radio, then two-way contact between civilizations is essentially impossible, not because of hostility and not primarily because of distance, but because of scheduling. The interval during which a civilization is both detectable and interested in being detected is shorter than the light travel time to anyone who might notice. A signal arrives at a destination that stopped listening before the signal was sent. That is the 100-year window from the previous entry, with the ending replaced. Nobody died. The room simply emptied on a timetable. And from far enough away, an emptying and an ending produce exactly the same observation. Smart draws one further consequence that is worth noting because it inverts the usual anxiety. On this account, transmitting is not dangerous. It is pointless. There is nobody at the other end of the schedule to receive it. That is a considerably lonelier conclusion than the one at number 6, and it arrives without any hunters in it. It is worth pausing on how genuinely strange the picture is, because it is easy to hear this as a technical proposal and miss what it describes. Somewhere in this galaxy, on this account, there is a system that once held a world with weather and oceans and a species that named its own constellations. That species built instruments, and then better instruments, and each generation of instrument was smaller and faster than the last. At some point, the distinction between the civilization and its instruments stopped being useful. And then the whole thing, every memory, every argument, every piece of art any of them ever made, moved into a volume of space smaller than the building it started in, and kept going. From outside, nothing happened. The star still shines. The planet still orbits it. The atmosphere is intact and the oceans are there, because none of it was needed and none of it was harmed. If we pointed our best telescope at that system tomorrow, we would find a temperate world with an interesting spectrum and no sign of anyone, and we would put it on a list of promising candidates. That is what this theory says the galaxy looks like. Not ruins. Not silence after a catastrophe. Just a very large number of ordinary systems, each of which finished, quietly, and left the furniture. So, have we looked? Only obliquely, and mostly for the wrong signature. Every search discussed on this list has been designed to find something being built, something being broadcast, or something radiating waste heat. A civilization that has gone inward is defined by producing none of those. The observation that would count is a statistical one about which stars are quiet and how old they are, and assembling that dataset properly is the work of the next few decades rather than the last few. Every theory so far has proposed a single specific barrier. The next one proposes that there is exactly one barrier somewhere along the path, that we do not know where it is, and that everything depends on whether we have already passed it. Number 2, the filter. In August of 1996, an economist named Robin Hanson posted an essay on his university webpage. He revised it through September of 1998 and then left it there. It was never submitted to a journal. It has never been peer-reviewed. It is about 4,000 words long, and it is one of the most consequential pieces of writing anyone has produced on this subject. Its opening move is simple enough to state in 3 sentences, and everything else follows from them. Humanity appears to have a non-trivial chance of expanding to fill the universe with lasting life. The space near us appears to be dead. Therefore, any given piece of dead matter faces an astronomically low probability of producing that outcome. There exists, somewhere along the path from dead matter to expanding lasting life, a great filter. And the only question that matters is how much of it is behind us. Hansen laid the path out as a sequence of roughly 9 steps. A star system with the right conditions and the right organic material. Reproductive molecules, chemistry complex enough to copy itself. Simple, single-celled life. Complex, single-celled life. Sexual reproduction. Multicellular life. Tool-using animals with large brains. Our current stage, whatever that is. And finally, the colonization explosion that fills a galaxy. Each of those is a candidate barrier. And the product of their probabilities has to come out small enough to explain what we observe, which is nothing. That is the entire argument. It is a piece of arithmetic with a fork at the end. It is worth walking the arithmetic once, slowly, because the argument is often described as gloomy when it is in fact just multiplication. Take a galaxy with, say, 100 billion stars. Suppose a fifth of them have a temperate, rocky planet, which is roughly what the exoplanet surveys imply. That leaves 20 billion candidate worlds. Now assign a probability to each of the 9 steps and multiply them together. If the product comes out at 1 in a million, then 20,000 civilizations should have arisen in this galaxy, and the sky should be extremely busy. If it comes out at 1 in 100 billion, then the expected number is a fraction of 1, and a silent sky is exactly what you would expect. The gap between those 2 scenarios is 5 orders of magnitude spread across 9 terms, which is about a factor of 3 per step. That is the entire disagreement in this field, and nobody can currently narrow it because we have measured precisely 0 of those 9 probabilities. We have one example of each step happening and no examples of any of them failing, which is the least informative dataset a statistician can be handed. The fork is what makes this the second to last entry on the list. If the filter is behind us, then one or more of those early steps is fantastically improbable. We cleared it by an accident so unlikely that it has essentially never happened elsewhere. We are among the very first, perhaps the only, and the path ahead is wide open. If the filter is ahead of us, then every civilization that cleared the steps we have cleared went on to encounter a barrier we have not yet reached and did not survive it. Every single one. Without exception. Across 13 billion years, both branches are consistent with everything we currently observe. That is the whole problem, and it is worth stating as plainly as possible. The silence is equally good evidence for both readings, and the 2 conclusions could hardly be further apart. One of them says we are extraordinarily lucky. The other says we are extraordinarily doomed, and the observation that supports them is identical. Hansen drew one practical consequence from this, and it became widely known through an essay Nick Bostrom published in Technology Review in 2008 under a title that gave the argument away, why he hoped the search for extraterrestrial life would find nothing. The reasoning runs like this. Suppose we find life on Mars. Not contamination from our own landers, and not material blasted off Earth by an impact and carried across, genuinely independent life, with a separate origin. That would be, on any ordinary reading, one of the most significant discoveries in the history of the species. It would also tell us that the origin of life is easy. It happened twice in one solar system, which means it is not rare. Which means abiogenesis is not the filter. And every early step we rule out as the filter transfers its probability to the steps that remain, and the steps that remain are the ones ahead of us. On that reasoning, the best possible news the exploration of the solar system could deliver is a long, boring series of empty results. Every sterile world is a small mercy. Europa dead, Enceladus dead, Titan dead, Mars dead. Each one is a quiet reassurance that the hard part might already be behind us. It is also worth being precise about what would actually settle the Martian question, because the popular version of it skips the hard part. Finding organic molecules on Mars would not do it. Organic molecules arrive on meteorites and form through ordinary chemistry. Finding structures that look like microfossils would not do it either. Mineral processes produce shapes that mimic cells convincingly enough to have fooled careful people more than once. What would settle it is biochemistry. A sample analyzed in a laboratory on Earth, examined for whether it uses the same coding system, the same amino acids, the same handedness of molecules that terrestrial life uses. If it matches, the two biospheres are related, and material has been traveling between the planets for 4 billion years, which we already knew. If it does not match, different code, different chemistry, different handedness, then life started twice in one solar system, and the implications run all the way through this entry. That is why sample return is the mission that matters here, rather than any lander. And it is why the outer solar system is arguably a better venue for the question. The subsurface oceans of Europa and Enceladus are far more thoroughly isolated from Earth than the Martian surface has ever been, so anything found there is much more likely to have an independent origin. The Europa Clipper spacecraft, launched in October of 2024, is on its way to the first of them now. It is a genuinely strange position to hold, and it is worth noticing how much it inverts the usual emotional shape of exploration. The people arguing this are not hoping for disappointment. They are hoping that the disappointment means something. Now the candidates for a filter behind us, because they are specific and they are checkable. Complex cells appear to have arisen exactly once. We touched on this at number 5, and it belongs here in its full form. Every plant, animal, fungus, and alga descends from a single event in which one simple cell ended up inside another, and the arrangement became permanent. That produced mitochondria. And Nick Lane's argument for why this is a genuine bottleneck rather than an accident of which lineage happened to survive is energetic and quantitative. A simple cell generates power across its outer membrane, and that membrane's area does not scale usefully as the cell gets larger, so there is a hard ceiling on how much energy is available per gene. Mitochondria removed the ceiling by moving power generation inside, into structures that can be multiplied at will. The difference in energy available per gene is on the order of tens of thousands of times. Without that arrangement, a cell can be efficient. It cannot be large or complicated. And in 4 billion years, across every environment this planet offers, every ocean, every hot spring, every rock face, every ice sheet, it happened once. Oxygenic photosynthesis appears to have arisen once as well in the ancestors of cyanobacteria. Every plant on this planet is running borrowed machinery. Chloroplasts are descendants of captured bacteria, exactly as mitochondria are. The single most consequential chemical innovation in the history of the biosphere, the one that filled the atmosphere with oxygen and made everything after it possible, has one origin. And substantial tool use of the kind that leads to metallurgy has arisen once. Not tool use in general. Crows shape hooks, octopuses carry shelters, chimpanzees fish for termites with stripped twigs. But the kind that compounds, that produces tools for making tools, that leads to smelting and then to everything else, has happened in one lineage, in the last few 100,000 years of a 4-billion-year run. There is a fourth candidate that gets far less attention than it deserves, and it sits in the middle of Hansen's list, where nobody looks. Sexual reproduction. It appears once, in the eukaryotes, and it is not obvious that it had to appear at all. It is expensive, it requires finding a partner, it halves the genetic contribution of each individual, and it breaks up combinations of genes that were working perfectly well. What it buys is speed. Recombination lets a population explore variation far faster than mutation alone, which is why sexual lineages adapt to changing environments and parasites in ways asexual ones cannot match over long spans. Without it, evolution still works. It simply works much more slowly, and a planet whose biosphere adapts slowly is a planet whose biosphere runs out of time. A world where that innovation never occurred might have life for 10 billion years and never produce anything more complicated than a mat. The last step on Hansen's list is different in kind from all the others, and this is worth noticing because it connects the whole argument to everything above it on this countdown. The first 8 steps are evolutionary events. They happen or they do not, and nobody involved decides anything. The 9th step, the colonization explosion that fills a galaxy, is not an evolutionary event. It is a decision taken by a civilization that has the capability and has to choose to use it. Which means the 9th step is the one that is sensitive to every argument at numbers 6, 4, and 3. A civilization that concludes silence is safer does not take it. A civilization that ends inside its own window does not reach it. A civilization that turns inward has no interest in it. The last barrier in the sequence is not a wall in the environment. It is a fork in the road, and the theories we have already covered are descriptions of the ways a species might choose the other branch. 3 one-time events, plus one that is arguably a fourth. Any of them could be the filter. Some combination of them almost certainly is, if the filter is behind us at all. Set against those, the strongest counterweight arrived in February of 2025, and we met it at number 5, the reassessment published in Science Advances by Dan Mills, Jennifer McAlady, Adam Frank, and Jason Wright. Their argument attacks an assumption buried in the hard steps model, rather than any of its individual claims. The model assumes that Earth was a suitable venue for each transition throughout its history, that the stage was set the whole time, and the actors simply took 4 billion years to show up. If that assumption holds, then a long delay before a step implies a low probability per year, which implies a hard step. But if the planet had to change before each step became possible, if oxygen levels, nutrient availability, ocean chemistry, and global temperature each opened a window in sequence, then the delays are measuring planetary evolution rather than biological improbability. And when you line each transition up against the window that permitted it, each one occurred reasonably promptly once its window opened. On that reading, the filter behind us shrinks considerably. Which, by Hansen's own logic, is not good news at all. Every unit of improbability removed from the past is a unit relocated to the future. That is the uncomfortable symmetry at the heart of this entry, and it is worth sitting with rather than resolving. The better the news about how life began, the worse the news about how it ends. Now the question this list keeps asking, and the reason this theory sits at number 2 rather than higher. A filter leaves nothing. That is not a limitation of our instruments. It is a property of the thing itself. A step that did not happen produces no artifact, no ruin, no isotope, no signal, no layer in any rock anywhere. There is nothing to find, because the defining feature of the event is that the event did not occur. Consider what that means observationally. A planet that stalled at simple cells for 6 billion years would have a thick, anoxic biosphere and an atmosphere full of methane and carbon dioxide. From 40 light-years away, with the instruments we currently possess, that planet is indistinguishable from one that stalled at chemistry, which is in turn indistinguishable from one where nothing ever happened at all. We cannot presently take a spectrum of a temperate rocky planet orbiting a sun-like star. Not a poor spectrum, any spectrum. The capability does not exist. It is being built. The extremely large telescope is under construction in the Atacama Desert in Chile, with a segmented primary mirror 39 meters across, larger than the collecting area of every existing large optical telescope combined. And the Habitable Worlds Observatory is the mission concept designed specifically to do this job, to block the light of a star well enough to take the spectrum of an Earth-sized planet beside it, and to do it for enough planets that the answer means something. Until those instruments exist and have been pointed at a large sample, the filter is not merely unproven. It is unaddressable. There is no experiment currently available that bears on it. And there is one final thing to say about this entry, which changes how the whole list should be read. The Great Filter is not a rival to the 9 theories above it. It is the container that holds them. Gamma-ray bursts could be the filter. The oxygen bottleneck could be the filter. The 100-year window could be the filter. Self-replicating machines could be the filter, if they exist, and if they do what the darker version says. Any of the mechanisms on this list, or several of them acting together, or something nobody has thought of, could be the barrier the arithmetic requires. The budget image is worth taking literally for a moment, because it is the clearest way to hold the whole list in mind at once. The silence has a price. Somewhere along the path from dead matter to a galaxy full of life, a certain amount of improbability has to be paid, and the total is fixed by the observation that the sky is empty. Every theory on this countdown is a proposal about which line item carries the cost. Number 9 says the bill is paid by sterilization. Number 5 says it is paid by chemistry and by air. Number 4 says it is paid by us shortly. And each proposal that turns out to be wrong does not reduce the total. It just moves the charge somewhere else on the same invoice. Hansen's contribution was not a mechanism at all. It was the observation that the silence sets a budget. Something along that path is extraordinarily unlikely or extraordinarily lethal. The budget has to be spent somewhere, and we do not get to choose where. He noted, 20 years after writing it, that the phrase had spread to hundreds of thousands of pages across the internet, while the underlying argument was rarely engaged with quantitatively. That is worth registering as its own small piece of evidence about how ideas travel. The frightening summary went everywhere. The 4,000 words that support it, with their careful conditionals and their explicit acknowledgement that every probability in the argument is a prior dressed as an estimate, mostly stayed on the university webpage where they were posted. A final word on the epistemics, because this entry more than any other depends on numbers that are not measurements. Every probability in the Great Filter argument is a prior dressed as an estimate. We have one biosphere, one origin of life, one instance of complex cells, one technological species. A sample size of 1 does not let you calculate a rate. It lets you construct a story about a rate and then attach a number to the story, and the number inherits all the uncertainty of the story without displaying any of it. that is not a reason to discard the argument. It is a reason to hold its conclusions loosely and its structure firmly. The structure is sound. If expansion is possible and the sky is empty, something along the path is very unlikely or very lethal. That much follows. Everything past it, which step, how unlikely, whether it is behind or ahead, is inference from a single case, and the honest practitioners in this field say so in their own papers, usually in a paragraph near the end that does not make it into any summary. So, have we looked? We have not been able to. That is the honest answer for this entry, and it is the only entry on the list for which the honest answer is that the search has not started. There is one theory left. It is the only one on this list that says the filter is neither behind us nor ahead of us, because on this theory, almost nothing has happened yet. Number 1. The graves that are not filled yet. Everything above this entry assumed that the galaxy is old. It is not. It is new. And the case that it is new is the strongest and the least discussed answer on this entire list. Start with the stars nobody counts. Red dwarfs, the class astronomers label M, stars with less than about half the mass of the Sun, make up roughly 3/4 of all the stars in the Milky Way. 3 out of every 4. And not one of them is visible to the naked eye from Earth. Every star you have ever looked up at and seen belongs to the minority. They are dim because they are small, and they are small in a way that changes everything about how they burn. A large star runs its fuel hard and burns only the hydrogen in its core. A red dwarf is so thoroughly convective that its entire body circulates through the fusion region. It uses essentially all of its fuel, and it uses it slowly. The result is a main sequence lifetime running from about 1 trillion years at the top of the class to something like 10 trillion at the bottom. Proxima Centauri is the nearest star to the Sun, 4.24 light-years away. It is a red dwarf, and it is expected to burn for roughly 4 trillion years. The Sun has about 5 billion years remaining. Proxima has a lifetime 800 times longer, and Proxima is not remarkable. It is an ordinary member of the most common class of object in this galaxy. Now set that against the age of the universe, 13.8 billion years. If life is possible around red dwarfs at all, then the era during which life can exist in this universe runs to something on the order of 100 trillion years. And 13.8 billion against 100 trillion is roughly 1/100th of 1%. We are living in the first 1/100th of 1% of the habitable history of the universe. Abraham Loeb, Rafael Batista, and David Sloan worked out the formal consequence of that in 2016 in a paper on the relative likelihood for life as a function of cosmic time. They integrated the probability of life emerging across all stellar masses and across all of cosmic history, and asked when that probability peaks. It does not peak now. It peaks around 10 trillion years from now, around stars of about 1/10 of a solar mass, and it is higher then than it is today by a factor of roughly 1,000. Their word for life at the present cosmic epoch was premature. Consider what that implies about our position. If you selected a random observer from across the entire span of time during which observers can exist and asked when they lived, the answer would not be now. It would be trillions of years from now, on a world orbiting a small red star, at a moment so far ahead of us that the Sun will have been a cooling ember for 1,000 times longer than it ever shone. We are not late to this. We are early. Extraordinarily early. There is a second, stranger piece of timing at the other end of history, and it deserves a moment because it establishes that habitability is a function of cosmic time in both directions. Loeb pointed out in 2014 that when the universe was between about 10 and 17 million years old, the cosmic microwave background, the leftover heat of the beginning, which today sits at 2.725 Kelvin, a few degrees above absolute zero, had cooled to between roughly 273 and 373 Kelvin. Which is to say, for a few million years, the temperature of empty space, everywhere in the universe, was in the range where liquid water is stable. Not on planets. Everywhere. No star required. No orbit required. No habitable zone, because the entire universe was one. The obstacle was not warmth. It was chemistry. Heavy elements barely existed at that point. The first stars had only just begun manufacturing them, and there was almost nothing to build a planet out of. The window was real, and it was almost certainly empty. But it happened, and it is worth 30 seconds of anyone's attention, because it means the universe has already had one era of universal habitability, spent it on nothing, and has another one, vastly longer, still ahead. Now, the argument that gives this entry its edge. Brandon Carter published it in 1983 in the Philosophical Transactions of the Royal Society, and he began from a coincidence that had been sitting in plain view. The time it took this planet to produce a technological species is about 4.5 billion years. The total main sequence lifetime of the Sun is about 10 billion. Those two numbers are within a factor of 2 of each other. There is no physical reason they should be. The rate of nuclear fusion in a stellar core is set by gravity and quantum tunneling. The pace of molecular evolution is set by chemistry, ecology, and chance. The two processes share no mechanism, no scale, and no common cause. They should differ by many orders of magnitude in either direction. Carter reasoned through the possibilities. If intelligence normally arises quickly, in millions of years, then Earth took 1,000 times longer than typical, which is a strange thing to be. If the two timescales are genuinely matched, it is a coincidence with no explanation. So he took the third option, that the biological timescale is normally very much longer than the stellar one, and that what we are seeing is a selection effect. On almost every planet where this process could run, the star dies first. The process is cut off partway through, and nobody is left to notice. The only worlds that produce observers are the rare ones where the sequence happened to finish in time, and every observer, everywhere, necessarily finds themselves on one of those. We are not looking at a typical outcome. We are looking at the only kind of outcome that can look at anything. That is a genuinely uncomfortable argument, and it stood more or less unchallenged for 40 years. And then, in February of 2025, it was challenged directly. This is the third time the reassessment in Science Advances by Dan Mills, Jennifer McAlady, Adam Frank, and Jason Wright has come up on this list, and this is where it matters most. Their argument is that Carter's coincidence dissolves if planetary conditions, rather than improbability, set the pace. Earth's major transitions were gated. Oxygenation had to happen before large active animals were possible. Ocean chemistry had to change before certain metabolisms could work. Nutrient availability and temperature each had to reach particular ranges. And when you line each transition up against the gate that permitted it, each one occurred reasonably promptly once the gate opened. On that reading, the 4.5 billion years is not a measure of how unlikely we were. It is a measure of how long the Earth took to get ready. And if that is right, then intelligence is not a lottery that almost every planet loses. It is a process that almost every planet has not finished, because almost every planet has not had time, and because almost every planet orbits a star that will still be quietly burning long after the Sun has become a white dwarf and cooled to nothing. There is a piece of context that makes the earliness concrete rather than abstract, and it concerns what the universe had to build before any of this was possible at all. The first stars formed within the first few 100 million years after the beginning, and they were made of hydrogen and helium and essentially nothing else, because hydrogen and helium were essentially all there was. Those stars could not have rocky planets. There was no rock. Every atom of silicon, oxygen, iron, carbon and magnesium in every stone on this planet was manufactured inside a star that formed, burned and died before the sun existed, and was scattered by its death into the gas that eventually became us. So the universe spent its first several billion years assembling the raw material for planets before the first planets like this one could exist. Rocky worlds are a late development. Life on rocky worlds is later still. And the manufacturing has not stopped. Every generation of stars enriches the gas a little further, and the planets forming now are built from a richer mixture than the Earth was. That is a large part of why Berewsian peoples reached the number they did, and it is why the earliness argument does not depend on any exotic assumption. It follows from ordinary chemistry running on a cosmic schedule, which produces the reframe this entire countdown has been walking toward. The galaxy is not a graveyard. It is a room that filled up early with a handful of guests, and it will fill properly much, much later. Peter Berewsi and Molly Peoples put a number on that in 2015, working from the star formation history of the universe and the rate at which planets are still being assembled. Their estimate was that roughly 92% of the Earth-like planets that will ever exist have not yet formed. 92%. The overwhelming majority of the worlds that will ever hold an ocean are not there yet. The material is still in gas clouds, still in the shells of stars that have not exploded, still being sorted by processes that will take billions of years to finish. We are not the last ones. On this reading, we may be among the first. And being first is not an achievement. It is a position, and it is a lonely one. Let me put you somewhere, and then we will come back down the list. A temperate world orbiting a red dwarf, 10 trillion years from now. The star is small and deep red, and it does not move. The planet is tidally locked, so the star sits at a fixed angle above one horizon, and has sat there, unmoving, for longer than the Milky Way has existed. There is no sunrise on this world, and there never has been. The light is dim by our standards, and perfectly adequate by any standard that matters, and it is astonishingly steady, a furnace that has not varied appreciably in 10 trillion years and has 90 trillion left. Look up, away from the star, and there is almost nothing there. The local group merged into a single elliptical galaxy so long ago that the event is not recent history but ancient geology, and everything beyond it receded past the limit of visibility a very long time ago. The sky over this world is nearly empty. Whatever lives here, if anything lives here, has no way to know that other galaxies were ever visible to anyone. And the ocean below has had 100 times longer to do whatever oceans do than the Earth's ocean has had. Every process that took 4 billion years here has had 400 billion there, and still has room. That is the era. What we are living in is the opening minute of it. So, have we looked? For the last time on this list, here is the honest answer, and it is a real number. Project Hephaistos, led by Matthias Suazo and Eric Zachrisson at Uppsala, cross-matched the Gaia spacecraft's third data release against the two MASS and WISE infrared catalogues, across about 5 million stars within 300 parsecs of the Sun. They were looking for the waste heat that a partial structure built around a star would necessarily radiate, because whatever else a civilization does with a star's energy, thermodynamics requires it to release the leftover as infrared. The 2024 result identified 7 candidates. All 7 are red dwarfs. All 7 show mid-infrared excess consistent with material at somewhere between 100 and 300 Kelvin. 7 out of 5 million. And the follow-up work has not been kind to them. Archival diagnostics and higher resolution radio imaging of the strongest candidate have turned up background galaxies aligned by chance and ordinary dust and other natural explanations. None of the 7 is confirmed. Separately, the survey led by Jason Wright examined roughly 100,000 galaxies in the same infrared data, looking for waste heat on the scale of an entire galaxy, and found no galaxy reprocessing more than a modest fraction of its starlight. Those are real measurements with real limits, and what they establish is not that nobody is out there. It is that nobody has built at the largest scale anywhere we have looked yet. Now the counterweight, because it belongs in the finale, and because it is the one fact that could collapse everything I have just said. Red dwarfs may be uninhabitable. They flare violently for their first billion years. A single flare from a small star can outshine the star itself and deliver a dose of extreme ultraviolet radiation that would strip an atmosphere from a nearby planet. And planets in their temperate zones must orbit close in, which means they are tidally locked and bathed in that radiation for as long as it lasts. When the James Webb Space Telescope observed the innermost planets of the TRAPPIST-1 system in 2023, it found no evidence of thick atmospheres on either of the first 2. That is consistent with bare rock, stripped by the star. If that turns out to be the general case, then the trillion-year future is not available to life. The era of habitability is roughly the era we are already in. We are not early. We are it, and the silence is not a matter of timing. It is the answer. And there is a reasonable middle position that deserves mention, because the argument does not stand or fall on red dwarfs alone. White dwarfs, the cooling remnants of stars like the Sun, are also long-lived, and a stable one provides steady, gentle illumination for billions of years without flares. Because they are small, a planet passing in front of one blocks a very large fraction of its light, which makes such systems unusually easy to study. Whether a planet could survive its star's transition into a white dwarf and then settle into a stable, temperate orbit is an open question, and at least one candidate has been found. If red dwarfs prove hostile, the long future may still be available somewhere else, on a slightly shorter clock. It is also worth noting where this planet sits on that schedule, because the numbers are humbling in a way that has nothing to do with anyone else. The Sun has about 5 billion years left as an ordinary star. This planet does not. Rising solar output is expected to overwhelm the carbonate-silicate thermostat we discussed at number 5 within roughly 1 billion years, and complex life here will end long before the Sun does anything dramatic. Life has been present on Earth for about 4 billion years and has perhaps 1 billion remaining. We are not in the middle of this planet's biological history. We are near the end of it, on a world orbiting a star that is itself only middle-aged, in a galaxy that is barely getting started. And the galaxy will change around it. In roughly 4.5 billion years, the Milky Way and Andromeda will merge, not a collision in any violent sense, since the stars are so far apart that essentially none will strike another, but a gravitational rearrangement that will scatter the spiral arms and eventually settle into a single large elliptical galaxy. The red dwarfs will pass through that event almost entirely unaffected and keep burning afterward for trillions of years, long after the merged galaxy has stopped forming new stars altogether. The stelliferous era, the span during which stars shine at all, is generally estimated to run to about 10 to the 14th years. Everything in this video, all of recorded astronomy, sits in the first 10,000th of it. That question is open, and it is one of the few on this list that will actually be settled by instruments already under construction within the lifetimes of many people listening to this. So let us walk back down. We began with atoms. Number 10 was the only theory on this list whose evidence anyone has physically held. Iron-60 drilled out of Pacific crust, melted out of Antarctic snow, carried home from the surface of the moon. Number 9 predicted an event that leaves no fingerprint at all, and left none. Number 8 predicted machines in this solar system, and several deliberate searches found nothing. Number 7 predicted an archive inside every living cell, and we finished reading it 3 years ago and cannot yet interpret it. Number 6 predicted an absence and delivered one. Number 5 predicted worlds full of life that will never make a sound, and we do not yet have the instrument to check. Number 4 predicted ruins that fade within a few 100,000 years. Number 3 predicted a statistical shape in which systems are quiet. Number 2 predicted, by its own definition, nothing whatsoever. And number 1 predicts an empty record because the graves are not filled yet. 10 theories, and the amount of recoverable evidence fell, entry by entry, from a jar of atoms to nothing at all. That descent was the structure of this list. And here at the bottom of it is the thing that should be said plainly, because it is the real answer to the question the title asked. Nothing we can currently measure distinguishes a galaxy in which everyone died from a galaxy in which nobody has arrived. The same silence, the same empty spectra, the same 7 unconfirmed candidates out of 5 million stars. A graveyard and an empty room produce identical observations, and the only instrument that separates them is time. There is one more thing, and then we will finish. At the very beginning of this list, at number 10, we found that the shell of the local bubble, the wall of gas swept up by the 14 to 20 stars that exploded in this neighborhood over the last 13 million years, is the surface on which essentially every young star near the Sun is currently forming. The debris of the dead is the material of the next generation. The graveyard and the nursery, we said then, are the same object. That was a description of a wall of gas, about 400 light-years from here. It may also be a description of the galaxy. So the answer to where is everybody may not be that they are gone. It may be that this is early, that the room is nearly empty because the guests have not arrived, and that the specific loneliness of this particular century is not a permanent property of the universe, but a date on a calendar that runs for 100 trillion years. Which is, at the same time, the most reassuring and the loneliest thought on this entire list. There may be no filter behind us, and no filter ahead. There may only be a very long wait, and the peculiar privilege of being among the first to notice it. Let that sit with you for a while. The sky is quiet tonight, and on this reading, it is quiet because it is early. Sleep well, and good night.